just so that you all are aware, I do record these lectures because I teach online sections and in-person sections of this class. And so it just makes more sense for me to record once and post the recording of this class for my online students. It also really helps them, I've found, because I use a software called GoReact, where my online students can interact with each other while they're watching the lecture. And so if I'm talking to you in the classroom, and then I turn to the camera and I treat the camera like a student, a lot of my online students say that it feels like they're in the classroom and being involved here with y'all. So if I, at any point, address the camera, please don't look at me like I'm crazy. Understand I'm trying to be a good professor. All right? All right. Well, welcome to, oh, sorry, I got something in my eye. All right. Welcome to Geology. You're here. You made it. Could you do me a favor? What's your name? Sebastian? Do me a favor and close that door. Campus police walks by and I don't have it closed. They'll get on my case. Appreciate it. You all have your names written on your cards. Make them bright and bold. And then, is your name Sebastian too? Oh man, this is gonna be rough. Okay. And then go ahead and either lean them against a box like that or tent them so that I can see them from the front. Just like color it as dark as you can so I can see it from up here. It's really hard to see pencil from up here. So let's see who we've got. And by the way, my online students, go ahead and introduce yourself right now in the chat, in the GoReact chat. I'm going to go around and I'm going to look at all your names. And I want you to tell me where you're from. And I want you to tell me what your major is and something cool about yourself. And online students, go ahead and do that as well. All right, she's still writing, so let's start with you. What's your name?
Angel.
Angel, awesome. Angel, where are you from?
Puerto Rico, and something cool. I'm cool.
You're cool? Okay, well, that remains to be seen, doesn't it? I guess I'll decide that. Okay, I like it. Angel from Puerto Rico, you said?
Mm-hmm.
Awesome. How long have you been here?
I think I'm going to 3 years now.
3 years? Cool.
Yeah.
It's a little less than me. I've been here for 4 years. Cool. All right, and what's your name, ma'am?
Emily.
Emily, and where are you from?
I'm from Colorado.
Colorado. Where in Colorado?
Fort Carson.
Fort Carson. I lived in Longmont for about a month while I was getting training for a job I had in the past. I love Colorado. It's so beautiful. I would live there if the real estate wasn't sky high, honestly.
My major is business.
Uh-huh.
Something cool. This summer I went on a cruise.
Oh, where'd you go?
We just island hopped in the Bahamas.
In the Bahamas? Nice. I went on a cruise this summer as well. It was my first ever cruise I've been on. I went to Alaska. Took a helicopter up onto a glacier, spent the day up there, collected some samples, did some measurements. It was awesome. Not usually what you do on a cruise, I think, but I can't help it. I'm a scientist at heart. What's your name, ma'am?
My name's Lydia.
Lydia, where are you from?
From Odessa. I'm a STEM major. Something cool about myself is I'm trying to become an astrophysicist.
Love it. Astrophysicist. Please figure out black holes for me. I love them, but they keep me awake at night. Sebastian, where are you from?
I'm from here.
You're from here. Okay, what's your major?
My major STEM.
STEM?
Something cool. I don't know.
You haven't figured out anything cool about yourself? Has anyone ever told you you're cool for doing something or being something? You have great hair. Yeah, that's cool. I wish I had hair that good. It's hard work for me to keep my hair looking any semblance of good. What's your name?
My name is Aaron.
Aaron. Aaron. I'm sure you've heard that all the time. Okay.
Teacher specifically. I'm a STEM major, and something cool about me, I guess, is I like raccoons.
Raccoons. Okay. Cool. Why?
They're mischievous. I like the mischievous nature of them.
That's true. Okay, fair enough.
A little silly at times.
I have exactly one raccoon story, and I don't think you would like it. What's your name?
My name is Sebastian as well.
Right? Where are you
I'm
from?
from California.
Where in California?
Southern. Bakersfield.
Bakersfield. I was born in San Diego. Lived there for exactly 2 years, and I've never been back. So.
I was born and raised there. Lived here for 14 years. So
Got it. Cool.
I'm a petroleum engineering major.
Nice.
Something cool cool about myself is I play in a band.
Awesome. What do you play?
The saxophone.
Saxophone. Nice. Very cool. Do you play on the OC band?
No, it's my own band.
Okay. Have you ever thought about playing
No,
for
I don't
OC?
like that genre of music.
No? Oh, okay. Fair enough. Fair enough. Okay. There was something else I wanted to say. You're in a band. What'd you say before you were in a band?
I was a patrol engineer.
Petroleum engineer. That's what it was. I appreciate it when petroleum engineers actually take geology. I've met far too many petroleum engineers who thought they only needed to know engineering. There's a lot of numbers, but if you don't know the rocks, you can't be there. Yeah, exactly. And so people who actually take the time to learn the geology before they go and become a petroleum engineer, it makes geologists' jobs a lot easier because we don't have to do as much explaining on the spot to you, right? So thank you for being here. What's your name? What is it? Cade. Okay. I was like, Cade. Is that you, Clay, your last name? Okay, cool, 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 cool. So Cade, where are you from?
I'm born and raised here.
Born and raised here. What's your major?
Just general studies.
General studies. Do you know what you want to do?
I'm between like engineering and police officer.
Okay. Well, I like both of those. Those are both good. Something cool about yourself.
I'll be the first one in my biological family to graduate from high school.
Just graduate high school? Congratulations. How many of you here are dual credit students?
Oh, yeah, leave me out.
Yeah, you're the only non. Okay. Okay. Well, I expect you to set a good example. No, I mean, you should set a good example, but thank you for being here. Okay, cool. First one ever. That's fantastic. What an achievement. I am working on my PhD right now. I have a couple years left in it. It's going slow because I'm also teaching full time while I do it. It's a PhD in environmental science and policy, but I'll be the first person on either side of my family to ever get a PhD. So high school, I feel like, is kind of a bigger accomplishment than that because way less people get PhDs, but good on you, man. What's your name?
I'm Jocelyn.
Jocelyn.
My major is business.
Business.
What's your other question?
Where are you from?
Oh, I was born here.
Okay.
Born and raised in Odessa, and something cool about me is I love baking.
You love baking. What's your favorite thing to bake?
It depends if it's like muffins. I love baking blueberry muffins.
Okay.
And then if it's more like more creative, cakes.
Nice. Okay, now you're going into business and you love baking. Are you planning on combining those to?
Yeah, I wanna open my own.
You want to open your own bakery. I love it. That's a great plan. Fantastic. What's your name?
My name's Claudia.
Claudia?
Yeah.
Okay.
And my major is business.
Business as well. And where are you from?
Mexico.
Mexico. Where in Mexico?
Okinawa.
I'm going to pretend like I know where that is.
That's 3 hours away.
About 3 hours from. Oh, it's not that far. It's just across the border, then, about there. Oh, okay, cool. I have so many friends here who want to take me to Mexico, and I would love to go because it's shameful that I have not been to Mexico. I've spent so much time in this part of the United States. It would not be that hard, but I haven't done it. I've been to so many other countries. I've been to Germany, Austria, Switzerland, France, Scotland, England, Ireland, and Iceland, and I lived in Japan for 4 years. And somehow I haven't been to our next door neighbor. I've been to so much of Canada, but I haven't been to the southern neighbor. So I'm going to have to do that sometime. And something cool about yourself.
I want to be a lawyer of immigration.
An immigration lawyer. Fantastic. Way to take on today's issues, right? I love it.
My name is Zara, and I'm from Pakistan.
Pakistan. Okay, cool. We actually just hired an agriculture professor here who is from Pakistan. His name is Dr. Salman Mushtaq. He just started this semester. His family's still over there, but yeah, he works here at for OC now. So you should talk to him. I'm sure you guys will have so much to talk about. Okay. And Zara was your name?
Yeah.
Cool. What's your major?
Business.
Business. Okay, so this is the business corner. Are you also business?
Yeah.
It is the business corner. So we got the STEM corner, and you're thinking about engineering. So this is like the engineering, and then we've got the business over here. Okay, I don't know that I like clicks so much, but all right, that's fine. As long as we're still friendly with each other. I don't want to see any paper wads getting thrown across the room. All right. What's your name? Sorry, Oham?
Yes, sir.
Okay, cool.
Yeah.
And you're a business major, and where are you from?
I'm from Southern California as well. I'm actually from like LA County, so like Glendale.
Okay, yeah,
Yeah, and I moved out of there when I was like 4.
cool.
And something cool about me, I like to go golfing.
Oh, really?
Oh, yeah.
It's an expensive hobby, brother.
Yeah, but I mean, my friend put me onto it. I just use his clubs.
Okay, yeah, that removes a lot of the cost.
Mostly,
Okay,
yeah.
cool.
And what were the other questions?
I think that's
That's
it.
it, right?
Yeah, you like to
Okay.
golf. That's something
Yeah, I
cool
like
about
golf.
you. Awesome. Well, thank you so much for introducing yourselves. And for my online students, I look forward to reading your introductions later. As for myself, my name is Josh Hart. I have a bachelor's degree in geology from Brigham Young University in Rexburg, Idaho, a master's degree in geology from the University of Louisiana. And like I mentioned earlier, I am working on my PhD in environmental science and policy. Most of my research for my bachelor's and my master's degree is in paleontology. So I am a geologist, but in the subset of geology, I am a paleontologist more than anything else. My PhD, the reason why I'm doing my PhD in environmental science is because I'm kind of marrying my knowledge of how to analyze fossils to the data that we're getting from the results of global warming. And my hope is I can kind of combine those two, I guess you could say, different fields to come up with a better, not only explanation, but better educational materials that people in their everyday lives can understand the effects and future of global warming as it moves forward. We'll talk a lot about climate change in this class. There's a lot of misinformation about there. I'm just going to say this right now. Most of what you think you know about climate change is just out there because the news thinks that it sounds better than the truth. And you will be learning the truth as we understand it in science in my class. Okay? I'm not going to spoil future lectures here, but we will talk about that later on. All right? By the way, at any point, if you have questions about anything that I say, about myself, about my career, about anything in the class, about anything at all, except probably sports, I don't keep up to date with sports, so we can't really talk about that. But like, you know, current events in the news, mostly political, you know, global news, natural disasters, we can talk about that. This is an open forum classroom. I encourage you to ask questions. As a matter of fact, if you're not asking questions, you're doing science wrong. Okay? Please ask questions as often as necessary. Never feel self-conscious about it. Yes. Excellent start. Huh? Can you hold the snake? Absolutely, you can hold the snake. Absolutely. Let me just unwrap him a little here. It takes a minute. We don't want to force him. You found a nice comfortable perch. Okay, there we go. Have you ever held a snake before? Oh, I'm proud of you. Look at you go. All right, I'm just going to leave him there for a bit. You can feel free to pass him around if you want. Okay. This information here is kind of out of date. I haven't updated this PowerPoint in a little while, as you might be able to tell. I actually just celebrated my 9th anniversary earlier this month. Thank you. Thank you. I have 3 children. My oldest is Declan. He is 6 years old. He is in 1st grade at Compass Academy. This last Wednesday was his first day, and he's enjoying it. I have a daughter who is going to be 4 in November, and she is in pre-K right now. And then I have a son. My last is a son. He just turned 2 earlier this month as well. So I've got a 6, almost 4, and 2-year-old. And they keep me busy. When this job isn't keeping me busy, they keep me busy. So I have had a variety of jobs. But as far as the ones that are concerned in geology, I've done everything from gold mining in Nevada to petroleum geology in North Dakota, paleontology in Utah, Wyoming, Montana. That's what I was doing before I came here. I was the paleontologist babysitting the Keystone Pipeline. How many of you know what the Keystone Pipeline is? Raise your hand. You ever heard of the Keystone Pipeline? It was the big, massive pipeline project that Biden shut down the first day he was in office. Did you ever hear about that? That was the Keystone XL pipeline. They've been building it for 14 years. And he shut it down the first day in office. So As the election in 2020 was coming to a close, I saw the writing on the wall. I was like, I should probably not be working on this pipeline when he takes office. So I started looking for a different job, and I found this one, which is great because it gives me more time with my family, right? So plus, I wasn't one of the 11,000 people he laid off by shutting it down. What else? Yeah, I've done a bunch of jobs. The ones that I've enjoyed the most are probably the ones in paleontology. I found lots and lots of dinosaur bones. I will show you pictures of those as we move through the class. I found you can't actually keep a dinosaur bone after you find it unless it's on your privately owned property. All these digs that I was on, it was on either federally owned land or I was there with a permit from a museum, and so they belong to other entities. So no, I do not have any of the dinosaur bones that I found here to show you. I do have pictures that I'll show you. I have fossilized trees and a few other things that I found while I was out there, but none of the dinosaur material was anything I was legally allowed to keep. I do have dinosaur bones, but not ones that I found. Okay, ones that I legally purchased from the people who legally sold them to me for the department. Okay, we can just jump through all that. I always forget that I include all of that up there. That's the gold mine I worked at, by the way, right there. Okay, so again, this is an old PowerPoint, but the principle is the same. Y'all have done your Wrangler orientation and everything like that. If you're in my class, you're either a junior or a senior, or you're not even in high school, so I assume you've gone through Wrangler orientation in the past, but they always ask me to make sure that you check. By the way, this is something you're going to have to get used to. This is the third projector that they've given me in this classroom, and no matter what, it still flickers. And so some days you're going to see me whack that thing with a stick, and I'm not even joking. I will whack that thing, okay, to try and get it to work. I've tried wiggling the cord. I've tried doing everything. The best thing that they can figure is that somewhere along the way, the cord, the HDMI cord from the computer going up through the wall, through the ceiling, and into the projector, there's something wrong with that cord along that route. And the only way they could fix it is to rip up my wall and take out the cord. And they don't want to do that, so I have to just deal with it. Typical. Anyways, okay, so Wrangler orientation. We're all good with that. All right. Let's talk about Odessa College commitments. All right. There are some commitments that Odessa College expects from you and that I expect from you and that I will give to you that you can expect from me, okay? I commit to interact with you. It says by the end of the first day. I've already interacted with each of you, and I will continue to interact with each of you. I will go to you and ask for feedback and questions throughout the course of my class. Okay, for my online students, ask your questions in GoReact, and I will respond to them within 24 hours. Okay, that's my policy. I'll respond to your questions on GoReact within 24 hours. I will provide monitoring of student behavior that's in the classroom, as well as the assignments that you submit. If I notice that there's a definite decline in the rate at which one of you is turning in homework, I'm going to be like, there's something going on here. And I'm going to reach out to you to figure out what's going on. There might be something personally going on in your life. That's totally understandable. Please communicate that stuff to me, because I will notice if you start not turning things in. I'm going to be like, that's very out of character. And I'm going to reach out to you. But it's a lot easier if you just tell me that something's going on before we reach that point. That gives me a little more time to help you, okay, to figure something out, okay? I will have one-on-one meetings with you as often as you need them. I teach normally 60 to 70 students every semester, okay? So that's a lot of students for me to go to each one of you and set up a one-on-one meeting each week. So instead, it is in your hands. If you need tutoring, and this goes for my online students as well, if you need tutoring, you need to reach out to me and I will gladly schedule some time to meet with you, in person or virtually. My online students can come and meet with me in person if that's what you want. My in-person students, if you don't have the time to come back in and meet with me, we can meet virtually. We have that flexibility with our technology we've got today. See, he's curled up into a ball. That's why they're called ball pythons. Anyways, so tutoring, I don't have a geology tutor. I am my own geology tutor. So please reach out to me if you need help, and I will get you there. Okay? And then I have a highly structured course, as you will find out. And there are, in fact, some penalties for some behaviors that are not in accordance with my class policies. I will come to that later. Now, you commit to complete what you start. You are in my class today. You are capable of completing this class. By the end of today, you might be doubting that. But I promise each and every one of you is capable of completing it. Okay? I promise that. And especially if you involve me in that and you're communicating with me and asking those questions and getting that tutoring that you need, you will complete my class and you will get an A. Any old time you need them. I teach exclusively in the mornings. I do have afternoon meetings some days. So when you reach out to me and ask for tutoring, I will say, okay, I'm not available during this time, but I will have a time that I can meet with you, either sometime in the next few days. Okay, I will have a time that I can meet with you. All that's required is that you reach out and ask. Okay, you commit to attend class and attempt each assignment. It says attempt each assignment. Let me give you a little more clarity on what that means in my class. My labs, and for those of you that are here in person, you have discussion boards on Blackboard. For my online students, you communicate and discuss during these Go React lectures. You have exactly as many attempts as you could possibly want on those assignments. I do not cap you at 1 or 2 or 3 or 10 or 20 attempts at my labs. You have as many lab attempts as you want. Because a lab is a learning exercise. It's not an exam. I'm not going to restrict the number of times you can try to learn. Okay? So yes, you commit to attempt each assignment, but I just want you to be aware that means that you can attempt it as many times as you want. Okay? Don't just give up if you do a lab and turn in and think, I had no idea what I was doing. That's a loss. Don't think like that, because you can get feedback from me and do it again. All right? You commit to ask questions. Please do that. And use your student support resources. Odessa College has so many resources. Financial, food. We have counselors for, like, there are grief counselors. There are family mediation counselors. There's all sorts of services that Odessa College has. And if something is keeping you from performing well in this class and any other class that you're taking, please use those resources, because we want you in the best frame of mind possible to succeed. Okay? And then finally, you commit to develop well-organized, disciplined work habits. If you do not have good, healthy study habits right now, please try and develop them. And if you want some ideas, I'm happy to help you, but I will tell you right now, every person's study habits are unique to them. I can give you ideas for what works best for me. Please talk to each other about it as well. It's more likely you find something in common with each other than you do with my habits. But try and develop those. If you find yourself at the end of the day thinking, I did not get done anything or very little of the stuff that I needed to. I had 3 hours to work on this and I got 1 assignment done. That is the sign of maybe not healthy study habits. Try and experiment and find a way that works for you to do those assignments in the time that you give yourself. Okay? Any questions? Perfect. Okay. Each of you on Blackboard is going to see this. This is a written agreement that you will sign. Okay? It is the commitments. Okay? That should be on Blackboard there for you to look at and to sign. Also, there are a few other first day assignments that you do. There is an acknowledgement of class resources. This is something unique to my class. This is not something Odessa College requires. It is something that I require of you. I have had far too many students not do a darn thing in my class and fail as a consequence, only to go to my boss and say he didn't give me what I needed to succeed in the class. And so I've had enough of those conversations with my department chair and my dean that I made a list of all of the resources that I give you guys to succeed, including as much as my time as you need if you ask for it. It's all there on a list, and you each need to sign it, because now if a student says that, I pull up and say, really, you didn't know about all these resources that I gave you to succeed? Okay, I'm not saying any of you will be like that. It's just I grew tired of those conversations and being accused of that. So this is just what I do now. Okay. Let's see what else is on there. Oh, there's a first day assessment. Okay. This first day assessment is going to have a series of questions that are going to make you go, what? They may not even be geology related. They're vaguely scientific. They're all supposed to make you think. Answer them as best you can. Don't worry about getting any of them wrong, because that first day assessment, that is pass, if you complete it, no matter how well you did, you get the credit for doing it, okay? That is purely data for me to gather, to look at and interpret how you individually and as a class are thinking scientifically. That's a starting point for me to work with here at the beginning of the semester, and maybe know approximately where to push the bounds of our critical thinking in the class. All right. Let's see, anything else here? I'm going to go over all that in a second. Okay, we are going to have an hour and a half of lecture and an hour and a half of lab each time we meet. Typically, today's going to be different. There is no lab today because I have to go over this intro stuff. It's going to eat into that. So buckle up, guys. We got about 3 hours of lecture today. I know. The intro stuff is always the worst. I wish that I could give you like a 5-minute synopsis and then go right into the geology. I would far prefer that. But this presentation with me going over all this is an OC requirement, okay? So there is no lab assigned today. Your first lab will be assigned on Thursday, okay? But we will have a lecture about some geology here in a little bit. I hate timed exams. Who agrees? Yeah, timed exams are the worst. They really are. Because all you're doing is looking at that clock and thinking to yourself, this isn't enough time, or, oh, I've got enough time for that. And then X amount of time later, you're like, I don't have time for that anymore. That's all you're thinking about, okay? Just you and that clock. I absolutely despise timed exams as a college student, and I still do. But I am required to have a time limit on your exams. So each of your exams has a 500-minute time limit on it. That's the maximum amount Blackboard will let me put on an exam. Sound fair?
Yeah.
500 minutes. You have no exam that is more than 45 questions. That's about 12 minutes per question. And when you take into account that some of them are the true, false, or ordering questions, that'll take you 30 seconds. That should leave you plenty of time to do everything else. So you have the maximum possible time limit on all of your exams. Okay? Yeah?
Are the labs like writing a lot?
The labs include some writing, to be sure. Not like essay writing. I mean, if you're doing them on paper, you'll need a pen and pencil or something, but or typing if you're just doing them on your laptop. Most of the exams, or not exams, labs. Did you ask about labs or exams?
Did you ask about labs or exams?
Labs? Okay, yeah. The labs are going to be mostly identification based. I give you some samples that we have learned about in class, and using the ways that we've learned about identifying them in class, you are in turn going to identify them. Okay? So yeah, some writing, but only in as much as taking notes on what you found. Exams are different. Exams are a mix of what I call the usual suspects. That's short answer, multiple choice, true, false, matching, ordering, all of those, okay? But there will be some short answer format questions on the exams, okay? All right. My in-person class, you will have a discussion board each week. My online class, you don't have discussion boards, but you have these Go React lectures that I require you to participate in. How do you participate? I'm going to be asking questions during the class, just to the class or to individuals. Whenever I ask a question during the lecture, I want each of you to answer it. There, just type it in the Go React dialog box, okay? You need to do that with at least 3 of my questions. Also, you need to respond to at least 2 other student questions that are asked during that exam, and ask at least a question of your own. If my online students do all 6 of those things, you get full credit for participating in that lecture. Those of you that are here in class, not only do you participate by discussing these things with me, you also have a weekly discussion board, and that's where you get that same credit, okay? Cool. Some policies I have. You don't have a book for this class. No one was required to get a book for this class, right? I've had that as a problem in the past where they were like, wait, it was listed on the required materials, and I've had to go to the bookstore and have the same conversation over saying, I don't have a book for my class. I made a website specifically for my class. On that website, you have all the lab materials, you have all of the text on a textbook that's on there. Everything that you will possibly need for this class is provided to you for free. This is an OER class, online educational resources. I provide everything to you. Okay. The one exception is my online students who need to get the subscription for GoReact. But that's because it's interactive software and doesn't come free. Okay. All right. Please, no cheating. There are multiple forms of cheating. The one that I encounter most often is plagiarism. Who can tell me what plagiarism is?
Using someone else's work.
Using someone else's work and not giving credit, passing it off as your own. That's the crux right there. I use other people's work all the time. I gather someone's gathered data for 20 years of X, number of fossils that were found in this location. I don't have 20 years to collect those fossils myself, so I use their data. I use other people's work all the time. The difference is when I publish that paper, I make sure that person gets the credit for having collected that data. I'm not trying to say that I did it. By leaving out their name and what they contributed, I would be implying that I did that myself. Attributing the right way is how you avoid plagiarism. There are many things, labs, discussion boards, that I am happy for you to use other people's data in, other people's resources, including each other's, by the way. If you want to work in groups, please feel free. I encourage it. But say during an exam, it should all be you. Okay? And by the way, I have gotten very good at figuring out if it's not you. Okay? You don't want to be that person. I have, just in the last year, I think that I've expelled 3 students. The first time you get a warning and you fail that exam. The second time you are expelled from my class and I report you to the college. I have very, very low tolerance after having given you a warning about cheating. Okay? Also, I would appreciate it if you did not have your phones out in class. Okay? Just as a measure of respect to me and to yourselves and to the institution. Okay? You or your high school or OC or your parents, someone is paying for you to be here. And if you're on your phone instead of listening to me, you are disrespecting whatever person or entity that is. Don't let it go to waste. Don't take this for granted, my friends. College is something that not everyone gets to have. Everyone should, but not everyone gets to. And if you are lucky enough to go and get a bachelor's degree, that's even less. Master's degree, even less. Okay? Treat it with respect. And I appreciate your respect to me as well by giving me your attention. My last policy as far as classroom behavior is concerned, please no swearing. Okay? Respectful language, and there's a reason for that. You are here to better yourself intellectually. You are here to learn how to express yourself in a way that is far more mature than you have had in the past. Foul language is how the uneducated express themselves. It is how people who do not know how to use the right words speak. You are learning how to use the right words by being in college. And we're going to exercise that by refraining from using foul language in my class. We're trying to elevate ourselves here, right? Thank you. Okay. If you email me, I will always get back to you within 24 hours, with the one exception being holidays and weekends, because during those times, my family takes my priority. Okay? No, I'm not going to restart my computer right now. My family takes priority. I'm sure you can all understand that. I am here from 7:30 to 5:30, Monday through Friday. Saturdays, Sundays, and holidays, I give entirely to my family. Okay? That's not to say I won't answer you. if I have a minute, I just put my kids to bed on Saturday evening, I might open up my email and be like, oh yeah, okay, I've got 5 or 6 emails, I'll answer those, okay? But during the week, I will always answer you within 24 hours. You send it to me on Monday night, I will always get back to you either Tuesday morning or Tuesday afternoon after I teach the class, okay? I will always get back to you within that time period. Please, if you need to get a hold of me, email me. Do not use the Blackboard message service. You know what I mean by that? Yeah, when you go on the Blackboard page, okay, you open up Blackboard and it's got your content and it's got announcements and it's got calendar and it's got messages. Do not use messages. This goes to my online students especially, okay? Why don't I want you to use that? Yeah?
I was gonna tell you that my OC email has never worked since social media.
And you talk to IT about it?
To everyone who just can't reset my password.
Gosh, it's rough. Do you have a personal email?
Yeah, I have my personal.
Okay, are you comfortable using that?
Yeah.
Because let me tell you why I don't want you using this. They don't all get to me. Okay, I've had students send me messages on there and they don't show up for a week. Okay, there's something going on with that Ultra server that controls those messages. It's not super consistent, and I don't get a notification if you send me something on that. It depends entirely upon me opening up that messages tab to see if anyone messaged me on there. And I'm going to be honest, I forget. It's not there at the front of my mind. It's not easy for me to look at. However, you email me, boop, it's there on my phone. Boop, it's got a little pop-up on my computer if I'm in my office, okay? It's right there. I get a notification. It's at the front of my mind, okay? Please use email, not Blackboard messages. Cool? Cool. No. Okay, and then first day stuff. All right. Whew, that's done. Let's go to the more fun PowerPoint, shall we? Some of the slides at the front of this one are going to be a little recap, but there's some other stuff we need to talk about. This is a year out of date picture of my family, but those are my kids, and that's my wife. Love them. They're great. Actually, you will probably get to meet my kids at least, because every semester I have a silly geology movie night. So we meet here on a Friday evening and we watch a ridiculous science movie and make fun of it. And you get extra credit for being there. So it's fun. You bring food, you bring friends. I don't care if you bring as much family or friends food as you want. You can bring drinks too, as long as they're college appropriate. You catch my drift, right? Yeah, and it's just a good time. And I usually bring my kids to that, depending on the movie. If it's a pretty intense movie, I'll bring my oldest son. He's seen all of them. He loves natural disaster movies. Right now, he's obsessed with that Moonfall movie. You guys ever see that? It's totally ridiculous. And I have to tell him every morning, Declan, the moon is not coming closer to the Earth. But 6-year-olds, they're obsessed with the ideas like that. So, but yeah, he's seen all these movies, so he'll come. But if we watch something, a little more lighthearted, I'll probably bring the other two as well. All right, and we'll pick which day that we're going to have that a little bit later on. Here in a couple weeks, I'll send out a Google poll and have y'all vote. My online students, by the way, are also invited. Unfortunately, I cannot broadcast a movie to you. You would need to be here in the classroom to participate. It's against copyright law for me to broadcast it. But you do get the option of helping us pick the movie, and when the time is, hopefully some of you at least can make it. This is out of date. I still need to erase that. You do not need that book. It's all OER. I started that last year. However, that is my email right there. That is the best way to get a hold of me, okay? You can try calling my office. It's extension 6723. But if I'm not in my office, I'm not going to pick up. Email, I get on my personal device, my personal phone, right? So that's my email. Write it down any old time of the day. I may very well, like I said, I'm doing my PhD. I usually don't go to sleep until 1 o'clock in the morning most nights because I'm doing homework of my own. Okay, so I finish teaching. I go home at 5:30. I have dinner with my family, put my kids to bed 7:30 or 8. I usually spend an hour watching a show or something with my wife. She goes to bed around 9, and then it's just solid homework for me from like 9 or 9:30 to 1 in the morning most nights, okay? And then I'm up again at 6:30 to get my son to school. I'm exhausted by the end of the semester, just letting you know. But yeah, so you shoot me an email an old time of day, I'll probably still be awake, Okay. Our schedule is going to look something like this. Now, the one on the syllabus that you have is going to have the actual dates on it, but it's going to follow this format. Okay. We are going to cover certain material each day, and we're going to meet twice a week. In this case, Tuesday, Thursday. Okay. I don't think there are any holidays. Yeah, because Labor Day is on a Monday, so we don't have any holidays off for our class this semester. Okay. We've got Thanksgiving in fall 2, but that doesn't matter for fall 1. Okay. So week 1, week 1, week 2, week 2, week 3, week 3. This is the general format. You have this specific schedule and what we're talking about on your syllabus. Okay. But it's going to follow that twice a week format moving through the material. Your lab schedule is going to look very similar. We have 1 lab. We actually have 5 labs and 1 lab exam. So you're going to have lab material of some kind for 6 out of the 8 weeks. Okay. So there will be a few weeks when I don't assign a lab, one of them being the last week. I'm not going to give you any lab material because I want you to just be focused on studying for the final. But there's also going to be, after lab 4, there's going to be a random week where you don't have any material, and that just kind of allows you to catch up and redo assignments if you want. Okay. All right, your exams are worth 50% of your grade. Everything else covers the other 50%. Discussion boards, participating in GoReact, your labs, okay? The reason why I have it split like this is because I want passing my class to be achievable. Come on, camera, stay with me here. My camera has a basic AI in it, so I taught it hand signals, and it can zoom in on me. It will follow me around the room. Because I'm a very active person. In case you haven't noticed, I'm kind of a walker, like I mentioned, so I needed a camera that would follow me wherever I went. The reason why I have exams at 50% of the grade is because if you are better at doing your labs and discussion boards, if you're not really an exam person, then as long as you are at least eking out a D on an exam, let's say, as long as you're doing the work and doing the best you can and getting a reasonably okay grade on an exam, but you're really acing everything else, you're going to pass my class. The opposite is true. If you're really good at taking exams, but you're just not getting the labs, you just can't get a really good grade in the lab like you'd like, as long as you're doing well on your exams, you are also going to pass the class. The only way that you're ever going to fail my class, bless you, the only way that you're ever going to fail my class is if you're just doing poorly in everything. And if you're doing poorly in everything, that's a good indicator you should be coming to me and getting help. Okay? There's no reason why anyone who is here in this classroom or who watches my lectures online should ever fail my class. Most of the reasons why anyone fails my class is because it's the people who signed up for my class and then just never did anything. I have a few of those every semester. It sucks. I wish I could talk to them. It's also usually the same people who never answer my emails or phone calls. Okay, don't know what's up with that. Anyway, so your discussions are 20% of your grade, your labs are 30% of your grade, and there's a grand total of 6% total amount of extra credit possible. Where does the extra credit come from? Well, the assignments that you're going to do today, for one thing, your first day assessment, your acknowledgement of class resources, and the first day assignment. Those are all worth a few points of extra credit. The other 5%, okay, so 5% of your grade, or not of your grade, of, well, it could add 5% on top of whatever your final grade is, let's just say that, comes from your notes. I am extremely serious about strong note-taking skills. I'm so serious about note-taking skills that I incentivize you to make notes, okay? And I actually have, in every week on Blackboard, you'll see for both sections, online and in person, you'll see I have a submission folder for you to give me digital copies of your notes. And if you write them by hand, just snap a clear picture of it and submit it there, okay? I'm so serious about this, about notes being very important in the learning experience. I believe in what I call the 3-part learning method. You hear it, you write it, and you share it. If you hear something, if I tell you a chicken is blue, you're going to think, oh, that's weird. That's interesting. You will not remember I said that by the end of the day. If you write it down, my teacher said chicken's blue. That's weird. And every time you see that, you're going to remember that I said that. But then if you go home and you're flipping through your notes, you're like, oh yeah, my teacher said the chicken's blue. Mom, my teacher said that chickens are blue. That's going to stick a lot longer because that's going to spark a conversation about how ridiculous your teacher is, right? And then after your mom turns her back and goes back to doing whatever she was doing, you're going to Google chickens and make sure that they actually aren't blue because you're doubting yourself, right? So it's going to stay longer in your memory, okay? So you hear it, you write it, and you share it. And I'm encouraging that. I can only really control the first two parts of that. I can tell you something, and I can encourage you to take notes. What you do with those notes after that, hopefully you're sharing that information with people, right? But you are going to get extra credit at the end of the semester for having turned in your notes, as long as they follow two simple rules. There are two rules about your notes. They need to be clear. I need to be able to read them. How many of you is there anyone here who English is a second language? 3? Okay. Are you good at writing in English? Are you comfortable with that? Yeah? As long as it's something that I can tell that you're following along in the class, that's what matters. I want to look at your notes and be like, yeah, I mean, they took notes on pretty much every major point that I made, okay? Your notes should be something that you look at in 3 weeks from when you took it and go, oh yeah, that, not, what was that again? You know, you should write your notes in such a way that you can remember and draw upon that knowledge when you're looking at it. My second rule is they cannot be my PowerPoints. You can write down every word on my PowerPoints as far as I'm concerned. Heck, you can write down every word I say in class as far as I'm concerned. 2 years ago, I had a student who she recorded my class and then would go home and transcribe it on paper. Every word I said in class, yeah. Okay, and those were her notes. She ended up with a binder at the end of the semester that thick. Okay, now why was she being so serious about note-taking? Why am I encouraging you to be very serious about note-taking? That's where the second incentive comes in. I let you use those notes during exams. It's an open note exam in my class. Okay, that's the only resource I let you use. I know my class is hard. If I made it easy, then you wouldn't be getting the same education that you could get at any other college. And to help you get through my exams, I let you use your notes. And by telling you that you're going to be using your notes, you're going to take strong notes now, right? Yeah, we're all going to take good notes? Good, okay. Now, why are you here? You're here to learn science, specifically geology. Okay, you're going to learn a little bit more about that in a moment as to what geology is, but you are principally here to gain a greater understanding of your world, and by the way, something you're going to learn in this class, not just your world, but the universe itself, okay? But also, you're going to be gaining better critical thinking skills. What is critical thinking? Thinking harder? Deeper. Okay, I think we're getting there. What do you mean by deeper? Give me an example.
Memorizing it, you know, like, I don't know.
Asking the deeper questions.
Okay, so we're using that word again, deeper, but can anyone give me an example of thinking deeper about something?
Researching your topics on your own.
Ah, okay, researching topics on our own. If I jumped on CNN or Fox News right now, what would I see? On CNN, I'd see Trump's a moron. If I jumped on Fox News, I'd see Kamala Harris is a moron. I'm not trying to start a political debate here. I'm simply saying what? People are biased. So what is critical thinking? That is you making the effort to figure things out yourself, is essentially what it comes down to. Thinking critically about something is putting more effort into thinking about it than just surface level. If I were to just look at one of those headlines and go, oh, he is a moron. without going any deeper than that to figure out why people are calling Trump or Kamala Harris a moron in the first place, I'm not thinking critically, am I? I want you to not only listen to what I say about science, but appreciate that I am giving you the resources necessary to figure it out for yourself. If something doesn't make sense, if you're thinking to yourself, but wait, we learned about this thing, so how can this be true? Ask or look it up. I'd rather you ask because I can provide you a more simple solution than X number of PhD people online will, right? Who are not educators, right? You Google something about geology and you're probably going to come up with a different explanation than me. Not a wrong one, just one that is far more complicated than you care about in this scope of geology, okay? But I want you all to be thinking more critically as a result of being in my class. That's what it comes down to. I've structured my class to encourage that, to encourage you to understand and utilize the scientific method, which we will talk about today. Okay, we already talked about my class policies, my email policy. Before we jump into the actual geology, an hour in, right? It's been an hour. Yeah, it's been an hour. Any questions about anything we've talked about so far? Huh? Pretty straightforward. I appreciate that. Sound fair? Sound good? Feeling good? Okay, well then, here we go. How many of you have ever heard of geology treated like a joke? How many of you have ever watched The Big Bang Theory? I love it too. But every time Sheldon Cooper makes a geology joke, it's like a knife in my heart. He just twists it, right? If you haven't watched Big Bang Theory, do it. It's hilarious, okay? But there are comic strips and memes galore about what geology is, how much of a joke it is. Mostly, it stems around something along the lines of, they just look at rocks. Why is that interesting? Yeah, I know, right? You're going to know why, okay? That's why you're here, all right? What is geology? Well, the name geology itself is a combination of actually two words in Greek, geo and logos. Geo meaning earth, and logos meaning discourse or conversation. So the word geology itself, this is what I call Greek word math. They do this all the time, where they take two words and just throw them together and make a new word, okay? Greek word math, geology, is a conversation about the earth. Now, you can break that down into a bunch of other subcategories, okay? So a couple of examples. Ocean sciences involves geology. Why? Well, because the ocean bottom is made out of rock. What kind of rock? That's what we want to know, and that's what they study. Okay, paleontology, where I've spent much of my life, much of my professional career. Paleontology is what? Anyone know? Fossils. It's the study of, what are fossils remnants of? Huh? Animals, but also, it's not just animals, right? I've got a few fossilized trees up here. Not matter. Everything's made out of matter, except antimatter, I guess, but we won't talk about that today. It's for you to study, right? Life. Fossils are life, evidence of life. Paleontology is the study of the history of life on Earth, essentially, okay? Much more on that when we, if you take 1404 from me. We'll talk more about paleontology later in this class, but 1404 is the big one for that. Okay, so in this class, we're studying a lot about the physical characteristics of the Earth. 1404 is historical geology, and that's where we take that knowledge and intersect it with the history of life on Earth. So the things that you've learned about in the first class will make what you learn about in the second class make a lot more sense. That's why this class is a prerequisite to that one. Okay. Earth is what we call dynamic. Dynamic means characterized by constant change and activity. Give me an example of how Earth is dynamic. Weather, good. There are seasonal changes. That kind of comes down to like weather patterns and climate and whatnot. Still, yes. What else? Tectonic plates moving, perfect. If you don't know what tectonic plates are, you sure will. What else? Volcanoes, excellent. What are some things that we've experienced around here that are making people worried? Earthquakes. Bingo. Yep, we can talk a lot about the earthquakes around here later on. I haven't made this a public announcement, so don't go to the press with this or anything. I just made a partnership with the Lawrence Livermore National Laboratory in California. They are going to be providing me with data so that I can start a 2-year educational series here in the Permian Basin to let people know exactly why there are earthquakes happening here. That will start in January. That partnership was formed over the summer. Right now we're in the planning phase, and we will start things in January. So that's pretty exciting. There are a lot of earthquakes around here, and yes, they are connected to the oil field, spoilers. But we'll be distributing a lot of educational material about that here over the next couple of years. But yes, earthquakes are an example of how dynamic Earth is. Okay, so we got our earthquakes, things like landslides, tectonic plate movements, volcanism, okay? These are all easy to understand, easy to see, obvious examples of how the Earth is constantly changing. But are all changes necessarily going to be on that big scale? No. What other things could be happening? What other ways is Earth changing that may not be on that scale? Erosion and weathering. Okay, there's a difference between the two. You'll learn that. Huh? Okay, so changes in life, evolution, good. Okay, you were saying that. Okay, changes within life populations, excellent. Okay, so things like erosion, yes, weathering, changes in life, also lithification. Anyone know what that word is? Anyone want to guess what that word might mean? Lithification. It has to do with water, but it's not the main, the main thing in this word. Water is involved in this. Lithification is the name for the process by which loose sediment, like sand, becomes rock, like sandstone. That process is called lithification. We will talk about that at length later. But that's an example. It takes a long time, and it happens on a very small scale. Grains of sand getting squished together tight enough to make sandstone, right? Okay, so we've got our more global scale events and your smaller scale events, okay, micro scale events. All of these are example of how dynamic Earth is. I like to describe geology as a marriage between physics and chemistry. Yes, where biology is that favorite brother-in-law that comes to sleep on the couch all the time. Okay? Biology, you can have geology without biology. There are rocky planets in our solar system that have never had life on them, as far as we know. Mars and Venus are still, we haven't eliminated the possibility of life on either of those places. Mercury, highly unlikely. Pluto, almost definitely a no. Okay? But you can have rocky bodies with no life. And so biology isn't necessary to have geology. That's why I kind of described it as that brother-in-law, right? It comes to visit all the time on our planet, but it is not necessary for geology to exist. Physics and chemistry, though, are. You, hopefully, have had fundamentals of both physics and chemistry before coming here. I, as a matter of fact, am assuming that you did, because I will not be spending too much time explaining the fundamentals to you. I will mention the fundamentals, but I'm going to assume that you already took those classes. I don't have enough time in the next 8 weeks to give you a physics breakdown and a chemistry breakdown and teach you what I need to about geology. Okay? If you have questions about the physics or the chemistry, we can always discuss that later on, or I can refer you to the proper professor. But I'm just going to assume that you've had those classes up to this point. Okay? So let's start off with a brief history of the fathers of geology. Let's start off with actually science in general. How many of y'all have ever heard of this fella right here, Aristotle? Okay, Aristotle lived hundreds of years BC, okay? And he is what we refer to as a natural philosopher. Scientists didn't really exist at this point. What we term as science is something that is accomplished through a series of experiments that gives us quantitative data. Okay? Aristotle was a natural philosopher. This is a person who was smart enough and aware enough to ask questions about his natural world. But he didn't quite have the resources or the know-how quite yet to test those things. So at one point, someone came to Aristotle and asked him what a volcano was. Now, remember who Aristotle is, right? We've got the Greek pantheon is who everyone is considering as the reason behind everything on our planet at this point in time, okay? Everyone in that part of the world, I should say, okay? This group of gods, all of whom are responsible for something. So with the understanding in your head, the preconceived notion that all of nature and everything in your universe around you or in your perceived world around you is controlled or symbolic of a deity, a god, one of many gods, Aristotle assumed that volcanoes were passageways to the underworld controlled by Hades. Okay? I mean, when you look at a volcano, what do you see? It's a hole in the ground with fire coming out of it. To a Greek, hundreds of years BC, that's how you get to the underworld. That's a portal to the underworld right there. That makes perfect sense. So that's what he explained them as to be. Another time, someone brought him a fossil fish. So just a fish skeleton and a rock, right? It's fossilized, and said, "What is this?" Now, when you look at that, what do you see? You see what is obviously the bones of a fish inside of what is obviously a rock. And with your understanding at the time, what's your natural conclusion? There must be some species of fish that live in rock, and you found a dead one. That's the only explanation. He had no notion that there were animals that lived a lot long ago, and what would happen to the animals of a bone that was embedded in sediment for a long time. Okay, so that was an explanation that made sense to him. Natural philosophers, people who asked questions and attempted to answer questions, but only based off of what they understood at the time without using any scientific or quantitative data. Okay. Next up, we had James Ussher. Sorry, that's the wrong Ussher. This Ussher, okay? James Ussher was in the 1600s, okay? And he was an Anglican priest, okay? So Christianity has taken its hold on the world, okay? It's spread far and wide. He decided that he was going to go through the Bible and he was going to approximate ages of people and times between certain events and come up with, as best as he could find, how old the earth was. And he went through the Bible and he did it. And he published it, that the earth was created on October 22nd, 4004 BC. I don't know how many of you are Christian, but many Christian denominations today believe that the earth is approximately 6,000 years old. And it started with him. That's where it came from. Okay? Now, he used one source to come down to that conclusion, the Bible. Whatever stock you put into the Bible, and by the way, I need to put this out there. At no point in my class am I going to attempt to persuade or dissuade anyone towards or away from any already held belief system. I have my own. You have your own, whatever it may be. I will respect that. I will, however, be teaching science as we understand it, using the quantitative methods that we've discovered. Okay? If you would like to talk about where science and religion may intersect, I am happy to have that conversation in my office later. Okay? Okay. So he actually also said it was at 9:30 a.m. on October 22nd. I have absolutely no idea where he could have come down to 9:30 a.m. October 22nd, maybe. 4004, based on just the Bible alone? Sure, why not? Regardless, to this day, many geologists, myself included, still celebrate October 22nd as an ironic holiday. I don't think I think our semester ends on October 15th or 16th or something like that, which is a shame because if you were in my class, then I'd bring cake or something, or maybe I'd have you bring cake. You'd probably make better cake than me. But yeah, and we'd have a little party to celebrate Usher Day, is what we call it. But regardless, so why is this such a commonly held belief in the world today that the Earth is 6,000 years old? He came out with this, and the Catholic Church loved it. They went with it. What's happening in the world in the 1600s? What's happening? Let me give you a hint. What do England, Spain, France, and Portugal all have in common during the 1600s? What are they doing? They are colonizing the crap out of our planet. Okay? Those four nations alone went across the Atlantic and across Eurasia and were colonizing like nobody's business. And what were they taking with them? Christianity. And what was the brand spanking new doctrine that the Catholic Church has just adopted? That right there. And that is why the Earth being 6,000 years old is such a well-entrenched belief system in Christianity almost anywhere you go in the world today. Okay? Now, there were some people who kind of took issue with this. They said, well, if the Earth is only 6,000 years old, how do you explain all these big things? You know, how do you explain mountains? How do you explain these huge valleys? How do you explain volcanoes? How do you explain these things? And the answer to that was catastrophism. Catastrophism goes hand in hand with this, this 4004 BC date. It's kind of how they explained all that away. Catastrophism states that all of these large features on Earth must form during periodic but short-lived, extremely catastrophic events. A mountain risen in a few days as a result of an incredibly powerful earthquake. Volcanoes do not take a very long time to form, but an incredibly powerful eruption over the course of a week or two must make them. And that did satisfy people for a while, until enough time passed. Why? No one saw those things happening. Hundreds of years passes and none of those things happen that makes any of those features form in such a small period of time. People start to ask questions again. Someone who started asking questions was James Hutton. He was a Scotsman. By the way, if any of you ever get the opportunity to go to Scotland, highly recommend it. So many fathers of geology came from Scotland. That's not why I'm recommending you go. It's a fantastic country. I went because not only is it a fantastic country, but there are lots of geological things there I could look at. But James Hutton in Scotland started paying attention to processes, things that were happening over time. He spent most of his life collecting data. He didn't just make an observation and then go and publish it. He spent, I think it was like 27 years or something like that, collecting data. I'm talking like figuring out how much sediment washes down a stream over a given period of time. And doing that so often that you can come up with a very reasonable average amount of sediment that, you know, a stream can carry over the course of a year or two, right? What value could you find in something like that? Well, let's just say that your stream carries 1 ton of sediment downstream every year. And you go to the bottom of that stream where it empties out and all that sediment is left behind. And you do just kind of a general estimation of how much sediment is down there, how much sand is down there. And you come up with 100,000 tons of sediment is down there. How long has that stream been depositing sediment? 100,000 years. That's just an example, right? That's just one I gave you. But that's what he was doing. He was observing these processes to figure these things out. And he came up with a new date of creation, 210 million years, based upon all these years of data he collected. It was about 210 million years, if I remember correctly. That blew everyone's minds. They were like, no, no, there's no way Earth could be that old. There's no way. How is that possible? And where does God fit into that? Remember, Christianity is still a hype, right? Still is today, but yeah. What? Oh, we'll get there. Hold your horses. Okay? Now, this made a lot of problems. Christianity, they didn't like him. Okay? He got many threats. He was told, you don't step on our toes here. The earth is this old. He did it anyway. And as is unfortunately true with most scientific revolutionaries, he was not recognized, his contributions were not recognized until he was on his deathbed. A lot of them don't even get recognized until the scientists who came up with them are dead. He was practically dead when finally the scientific community was acknowledged, all right, he has some merit here. It's entirely possible he's correct. Okay? Now, his contributions through his observations are an incredibly powerful hallmark in the history of geology. But that is not the most important thing that he did. The most important thing, at least in this scientist's opinion, the most important thing that he did was give us what we call the principle of uniformitarianism. Now, other scientists had, in fact, developed similar statements to this. James Hutton was someone who kind of perfected and proved it, if you will. The principle of uniformitarianism. By the way, there are only 2 things in my class that I require you to know word for word. Memorize it, write it down. I don't mind how you do it, but you must know them word for word. Only 2 things. This is the first one. The principle of uniformitarianism. Physical, chemical, and biological laws that operate today also operated in the geologic past. I'll repeat that. Physical, chemical, and biological laws that operate today also operated in the geologic past. Today, in the geologic past. What does that mean? Someone interpret that to me. Make it English. Things that happen now must have happened in the past. Okay? And what does that do for us? By studying the way that our Earth works now, we can interpret the way that Earth was before. The same stream that's moving sediment downhill is the exact same thing, driven by the same physics, using the same materials, as streams 100 million years ago that were doing the same thing. By observing our Earth now, we can make interpretations about Earth's past. Very valuable in geology. But what else is implied here? And that's where I add on to this. Physical, chemical, and biological laws that operate today also operated in the geologic past and will operate in the geologic future. That's my own little addition onto that. It's more or less implied by the statement here, but I added on there myself, okay? So, by studying what we see today, we understand the past and can make some approximation for the future. It's a very powerful tool. That's a very powerful statement. Statements like this revolutionize science, make people think differently. Okay? An example of how this works is written down here. I kind of made it obvious. Small processes plus a long time, you'll get big results. It's like working out at the gym. Y'all have worked out at the gym, right? You go and you show up the first time with your limp noodle arms, right? And it's hard for you to do anything with a 5-pound weight, but you push yourself and you push yourself. A month later, you're moving on to the 10 or 15-pound weight. You don't got noodle arms anymore. You keep doing that exercise, right? A year later, You got the 35 or 40 pounders, and you got Popeye guns, right? That happens over time through each repetition that you go through. Earth is no different. It's the same principle. Here's an example. Our Grand Canyon. How many of you have been to the Grand Canyon? Okay, one of you. Highly recommend going sometime. It's incredible. You're standing at the top of a cliff, and a mile beneath you is the river. It's amazing. Okay, do it sometime. Okay? Yeah, the Colorado River is at the bottom. It's what carved that. The Colorado River carved this. We'll talk about why later on. But it didn't start as a river. It didn't start with a canyon. This is the end result. At some point, that river was a stream. And that stream eventually got more water. And that water eventually carved its way down into a canyon. Small processes plus long time. Principle of uniformitarianism has been true today as it is true in the past. Questions about that? No? Okay. Well, I'm sorry, brother. What was your name again with the snake?
Angel.
Angel, that's right. All right. Angel tried talking about this earlier. He jumped the gun a little bit. How old is the Earth today? Anyone know? The universe is 13.7 billion years old, as we understand it.
300 million, 400.
No. Our Earth is about 4.6 billion. I've rounded that. It's actually 4.543. Okay? But let's, for now, just leave it at 4.6 billion. Okay? That's generous rounding, but regardless. That's very old. That's even older than James Hutton thought it was. If they scoffed at him saying 200-something million years old, imagine what those people then would say what we know now. 4.6 billion? Billion is almost an unimaginable number. Now, we separate geologic time. Yes, absolutely. We separate geologic time into groupings, okay? These include eras, periods, and epochs, okay? Eras being the largest, and then periods being the smaller designation. Sorry, eons being the largest, eras being the next, periods, and then epochs, okay? Now, how do we differentiate these periods of time from each other? Where do we draw the lines? Okay, it depends upon a few things. We tell geologic time. We can figure out how old relatively something is using a few things. The law of superposition being one. What does the law of superposition mean? Something is older than another thing. When I have two things piled on top of each other, let's say I've got this cloth. It's work better if I fold it well. I've got this cloth and this orange cloth here. Right now, I'm holding them at the same level. But now, which one was there first? The orange one. How can you tell it was there first? I dropped it first. If all of you had turned your backs and not watched which one I dropped first, and you turn around and you saw them in this orientation, which one would you reasonably be able to say was there the longest? The orange one. Why? It's under the blue one. That is the law of superposition. Whatever's on bottom was there earlier. And therefore, we can look at rocks and give them designations relative in time to each other, because, say, the Permian there is older than the Triassic. Why? Because the rocks in the time period which we call the Permian are underneath that of the ones that we call as being in the Triassic.
Kind of like the layers of bark in a tree, right?
Like the layers in a tree, yes. Except the ones that are closer to the middle are older than the ones on the outside. Same principle, though. Okay? Okay. The next rule that we use to help with this is called the principle of fossil succession. How does this work? First of all, we've already established that layer A is older than layer B, is older than layer C, is older than layer D, is older than layer E, right? That's the law of superposition. But now let's say that my layers of rock have fossils. Let's say that each one of these layers of rock has a unique fossil present in it. Say fossil 1, fossil 2, fossil 3, fossil 4, and fossil 5. If I drill a hole right here and I find these 5 layers of rock, each have 5 individual fossils that I can identify as being present only in that layer of rock, and then I travel 100 miles that way, and I drill again, and I find a layer of rock that has one of those fossils, what can I reasonably construe? Sure, I can get a sense of the dimensional size of the ecosystem, of the habitat of that particular fossil. That's deeper than I'm looking for, though. I like how deep you went there, but that's too deep for the answer I'm looking for. Let's say, Yes, of course. Let's say that this layer of rock is limestone, which doesn't mean much to you right now, but let's just say that it's a type of rock called limestone. And then I travel 100 miles that way, and I find a layer of shale, which is a totally different kind of rock, but it still has that fossil in it. What do we know about that fossil? That fossil is not present in the layers of rock underneath. It's also not present in the layers of rock above. And yet both of these layers, here and 100 miles away, 2 different types of rock, each have the same fossil. What can I know for sure? That's the important one. The same time. Regardless that they are not in the same place, regardless that they are not the same rock, they both contain the same fossil that was only alive for a certain period of time. It wasn't alive before, and it's not alive after. Only during the time period that this layer of rock was deposited and turned into rock, was that alive. And even though 100 miles away, it's a different kind of rock, it still represents the same time. Are you following me? Anyone confused by this? Awesome. I love it. You're all sharp. Okay. That is the law. That is one of the best things we can get out of the law of fossil succession. There's actually more than that, but not necessary for us to talk about at this point. Okay. For now, let's just say the law of superposition helps us understand the relationship between layers of rock in a vertical sequence relative to each other vertically through our time scale, right? Or through a sequence of rocks that you see on the side of the highway, for example. The principle of fossil succession, we can use that to understand rocks not only vertically, but also across distances, horizontally, their relationship to each other. Okay? Gradually, that limestone became shale as the environment that it was deposited in became a different kind of environment. Maybe we had a near shore gradually moving out into deeper waters. But regardless, that organism was alive across that distance at the same time. And that's why it's present in both types of rock. Okay? Those are both very powerful. Now, if we want to talk about actual resolution of time, that's where radiometric dating comes in. And believe me, we will get to that shortly. For now, though, let's talk about how we use science. How does science work? Who can tell me the scientific method? Just off the top of your head. Anyone got that down? Let's start very basically. What's the first step? Don't look. Okay, what's the first step? Observation. What are you observing? Yeah, whatever. You're observing whatever you're interested in studying. Cade wears glasses. I have made an observation. Sorry to call you out. I also wear glasses, by the way. I have contacts in right now, though, because I hate wearing my glasses. Huh? Absolutely, yes. Okay. Cade wears glasses. I've made an observation. Yay. I'm proud of myself. Cool. What's the next step? I'll make a hypothesis. Why does Cade wear glasses? Well, I'm going to hypothesize that he wears glasses to be hipster. He thinks they're cool. He thinks they make him look cool. So he wears glasses. Okay, that's my hypothesis. How can I test this hypothesis? That's the next step, by the way. I kind of gave it away, but the next step would be to test it, right? How do I know it's true if I don't test it? So I'm going to test it. How can I test if that's why he wears glasses? Huh? Ask him? But that could give me a biased opinion. I need to actually test it. Okay. What you're implying here is that he may wear them for another reason. I like where your mind's at. Put different glasses on him. Say, hey, these glasses are cooler. Wear those. And if he puts those on and then starts bumping into stuff or running into walls, he may not wear glasses because he's hipster. I need to come up with a better hypothesis, a different hypothesis. What could another hypothesis be for why he wears glasses? He may have poor vision. How can I test that? We have a new hypothesis. Cade wears glasses because he has less than perfect vision. How can we test that? Okay, we're getting really mean now, but okay, we can do this. Yeah, okay, fair enough. We've already gone there, I guess. Take off his glasses and ask him to walk across the room. Is this bothering you that I'm using you as an example? Thank you. Okay, take off his glasses, tell him to walk across the room. Angel sticks out his leg and trips him. He doesn't see it, right? Yeah, exactly. Do a finger test. Ask him to read letters across the room, right? There are all sorts of things we can determine, and they would all come down to a certain conclusion of what? He needs glasses because he has less than perfect vision. Is that true? Okay. But we didn't know that was true unless we tested it. We were just taking your word for it, weren't we? Okay. Now, we no longer have a hypothesis. What do we have? What do we call a hypothesis that has been tested and not proven wrong? Theory. A theory is a hypothesis that has not been proven wrong. Yet. And this is where I'm going to bring in a vital part of this. In science, we do not try to prove ourselves right. Wait, what? Isn't that what all that scientists do? They're just trying to prove themselves right about things. No. True science is not done from the perspective of trying to prove yourself right. In true science, true application of the scientific method, you use what is called falsification. That is trying to prove yourself wrong. Why would we, as real scientists, be more focused on trying to prove our own hypotheses wrong than we are concerned about making sure they are right? Kinda. There's something we're trying to get around. It is implicit in everyone. Every single one of us has this thing. Bias. I made a thing, and I think it's the best gosh darn thing on this planet, right? Are you confident in the quality of your cakes? But other people will need to taste it to be sure, right? I may think that I sing well. Everyone else may have a different opinion. I am biased to think that I do. Right? For us to get around the problem of bias, we need to approach the problem from the perspective of, I'm already wrong and I'm going to prove it. I'm going to do everything in my power to make sure that this hypothesis is incorrect. And it's going to feel so good when I succeed. Because you know what you found if you succeed in proving a hypothesis wrong? If I prove a hypothesis wrong, I have found truth. This thing is incorrect. That's true. If I fail to prove it wrong, what have I found? If I have given it my all, if I've done my darndest, if I have tried for years and years to prove this thing wrong and I cannot, what have I found? I may have found truth. through falsification, the proper application of falsification in science, we are finding truth. What is science but the pursuit of truth? Truth about biology, truth about geology, truth about physics, truth about society, truth about psychology, truth about the creation of cells, truth about anything in science. We are seeking truth. We want to know and understand. Actually utilizing the scientific method, that gets us there. Because whether we prove a hypothesis correct or incorrect, we have still found truth. Whereas, if I approach it from the perspective of I'm already right and I'm going to show everyone else I'm right, I run the risk of publishing untruth, right? I could get data back that shows my hypothesis is incorrect, and my initial instinct will be that, oh, well, I must have done the experiment wrong. I'm going to change a few parameters and then run it again. And I'm not going to be satisfied until I get something that I can justify proves me correct. An unfortunate number of scientists in today's day do that. But they are shooting themselves and the progress of science in the foot by approaching it that way. Okay? Don't be those scientists, my STEM people. Okay? And everyone else too. This applies to everyone, no matter what career you're going into, right? All right. Any questions about the scientific method? Okay. Let's talk about Earth now. Let's start zoning in on our little blue marble here. By the way, this picture was taken, I believe, in 1979. This picture is called the blue marble. One of the most beautiful pictures ever taken, probably one of the most influential, significant pictures ever taken in the history of mankind. Okay? I can't imagine a more influential picture having been taken until the day someone is circling Mars and takes the picture themselves, or is circling, I don't know, some other planet somewhere else in another solar system and takes that picture themselves. No one was even over here. It must have been the ghost. You'll find out as you spend more time in this classroom that a paper towel dispenser will randomly just dispense towels, and I call it the ghost. The ghost walked by. Okay. So Earth is separated. We kind of separate the different components of Earth into what we call spheres. First of all, we've got our hydrosphere. This includes all water on Earth. Water in the atmosphere, water in the ocean, water in rock. Yes, there is water in rock, okay? All water on Earth is in the hydrosphere. About 71% of Earth's surface is covered in water. Did you know that? That's approximately the same amount of water that's in each of us. We're about 70% water, which makes us cucumbers with attitude, really, if you think about it. Okay, then you've got the atmosphere. Okay, the atmosphere includes all of the gases on Earth. Okay, this thin envelope of gas above the surface of our planet, that is our atmosphere. Very, very thin when you really look at it, compared to the rest of the planet anyway. Fairly thick compared to you and me. Matter of fact, that little orange strip of atmosphere, that's the top of the troposphere. Most planes don't even go over that. Okay? We mostly stay within that little small area. Okay? Then we've got the geosphere. That is all of the solid components of Earth, from the surface going down to the middle. Okay? And we will talk about those different layers inside of the Earth later on, but that is the geosphere. The radius of the Earth is about 6,400 kilometers from the surface to the middle, to the center. Okay? That's geosphere. And then the biosphere. That's all life on Earth. Everything. You, me, birds, fishes, bacteria. Okay? Now, the biosphere is cool because it's actually all the other spheres combined. Okay? You and me, we have minerals. We require minerals to sustain ourselves. Your bones are mostly calcium. Your bones are crystals of a calcium-based mineral. So are your teeth. Yeah, they break. When they break, they splinter, just like a rock does. They are made out of minerals. You and I are flesh and blood suspended on a framework of minerals. You've never been closer to geology before, have you? Okay, what else do we have? We inhale oxygen. But is it all oxygen? No, as a matter of fact, it's mostly nitrogen. We've got nitrogen, carbon dioxide, atmosphere, there's a little argon in there, right? This atmosphere we're inhaling, that's the atmosphere. Hydrosphere, I got it right here. 70% of me is hydrosphere. You and I and every other living thing on this planet are all of the spheres combined. It's interesting to think about, isn't it? Now, as all these spheres are interacting, come on, back up, there we go. As all these spheres are interacting, things happen. Life develops, for one, right? Also, things like weather phenomena, okay? Systems. A system is where energy is expended, and it can either be a closed system or an open system. A closed system is one where energy can enter, but matter does not leave. Mass does not leave. An open system is when both matter and energy can come in and out. Here's an example. Here's my water bottle. There is some mass in there. There is some matter. It is water, right? And there's also energy. That water's moving, therefore there's energy, right? I can take an electric diode and put an electric diode on each side and pass an electric current through this water bottle. Energy can come and go. Mass cannot. It's closed. If I were to open this and put an electric diode there, it would still be able to pass energy just like it would normally. But now if I turn it over, what happens? Matter can come and go. That is an open system. So when our spheres interact with each other, often it's going to be either through a closed or an open system, just like this water bottle. Okay. When that happens, we see the development of these things called cycles. A cycle is a repeating pattern that occurs as these spheres interact with each other and these systems are formed, where matter and energy are going to be transferring back and forth between these different spheres. The hydrologic cycle, you may know it as the water cycle, for example. Yeah, you may like going down your sweatshirt, by the way, just be careful. And if he does, just don't pull him out backwards, because otherwise his scales will go back the other direction, and that's very painful, okay? If he does go headfirst down your sweater or your shirt, just let him go all the rest of the way and pull him out down the other side, okay? Okay, the water cycle. Water comes and goes. I drink water, I dispose of water, it goes back out into the sewer system. Eventually, that water becomes purified again, goes out into the ocean, or it gets reconstructed and put back in our groundwater system. Whatever happens, okay? Rain falls. It is collected in a cistern, okay? Or it washes out to sea, where it joins the big mass of water again before it evaporates and comes back. There are many different aspects to the water cycle, but it is the recycling of this mass utilizing energy in the system. Same thing with the rock cycle, which we will learn about here in a little bit, okay? Now, all of this requires energy. Anything that happens, any of these systems, any of these cycles, they require energy, okay? There are two sources of energy, and these two sources of energy power different types of these systems. Any external cycle, things like weather, climate, which is essentially long-term weather changes, ocean circulation, so your tides, your currents, okay? Your erosional and weathering processes of rock and material, all of those derive their energy for those to happen from the sun. The sun sends energy down through our atmosphere. That energy is absorbed and utilized for different things. Without energy, there would be no motion, right? Nothing could happen. Now, the other source of energy actually comes from inside our planet. It's hot down there, in case you didn't know, right? That's why when some of that hot rock makes it to the surface, it becomes lava, right? It's extremely hot down there. Where does that heat come from? Well, some of it is definitely still from the fact that Earth started off as a molten ball of rock. Okay, so it's still extremely hot down there from back then, but also because most of our highly radioactive metals are very dense, they kind of made their way over time closer to the center of our planet. And so we have a lot of extremely radioactive material down there. That radioactivity generates heat, and that heat emanates out from the middle towards the surface. And so that's what powers our internal processes: volcanic eruptions, earthquakes, plate tectonics. Okay. So things like hurricanes, powered by sun energy. Things like volcanic eruptions, heat generated from inside the planet. That energy comes from inside our own Earth. Let's talk about the rock cycle. Rocks are made out of minerals. They are not interchangeable. Okay, talk more about this in a minute. Minerals are not rocks. Rocks are made out of minerals. Okay, I'll elaborate that on a minute, but for now, that's what a rock is. There are 3 types of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous rocks are made from lavas and magmas. Sedimentary rocks are made from sediment, like sand or silt or clay, these different muds, right? Chunks of rock like gravel that become compressed and turned into a new kind of rock, a sedimentary rock. Metamorphic rock is what happens when one of the other 2 types of rocks gets buried deep enough that it is heated and pressurized and changes its chemical and physical composition. Okay? We will actually spend chunks of time learning about each of these, starting with igneous rocks next week. Okay? Today is kind of just a general overview. Thursday, we're going to be learning about minerals. Next week, we learn about igneous rocks. So this is your rock cycle in a nutshell. Start off with magma. You can really start talking about this anywhere along the cycle. It just makes more sense to me to start with magma. So we start with magma, melted rock. We'll talk about why it's melted in the first place next week. But for now, we just have melted rock. And it starts to cool off, either on the surface or under the surface. It begins to cool down. What happens when it's liquid, when it cools off? It becomes solid, right? What does cooling off mean? It's losing energy. It's losing energy. It becomes more stationary. The atoms become more stationary. Therefore, you end up with solid. This cooling and crystallization results in igneous rock. That igneous rock is exposed at the surface. And while it's exposed at the surface, thanks to how dynamic our Earth is, it begins to weather and break down and erode, which means that the pieces are carried away. That weathering and erosion leads to deposits of sediment. Let's say sand. Okay, let's say we've got a whole bunch of sand. This sediment has been deposited as part of this process. What happens to that sand over time? More sand gets piled on top, and more sand gets piled on top, and more sand gets piled on top. What happens when you squish something hard enough? It compacts. And that goes through lithification, leading to the creation of sedimentary rock. Okay? That sedimentary rock continues to get buried deeper and deeper and deeper over long periods of time as more and more and more sediment and rock is piled on top of it. And once it reaches a certain depth, it is now at enough heat and under enough pressure that it causes a chemical change in the rock. Therefore, you go through the process called metamorphism. Your sedimentary rock has now become a metamorphic rock through this process. Metamorphic rock. Now, if your metamorphic rock continues to get buried deeper and deeper, eventually it will go through the barrier, that sort of heat barrier, before which it can get changed but not melted, and after which it is just straight up melted by all the heat. Okay? And when it passes that heat barrier, it becomes magma again. And we have completed our rock cycle. Now, you can skip a few steps here. There are some steps you can skip and it makes sense, and others that you can't really skip because it wouldn't make sense. For example, I can get this sediment, make sedimentary rock, and then instead of continuing to get buried, that rock can get exposed at the surface, and re-weather back into sediment. I can just recycle this part of the rock cycle over and over and over again. As a matter of fact, that happens all the time. Also, my igneous rock, instead of getting exposed at the surface where it will weather and break down into sediment, it could just get straight up buried again. What happens when it gets buried deep enough? It metamorphoses. I can skip this whole part if that igneous rock just gets buried again and it becomes metamorphic rock. Igneous rock, if it gets buried deep enough or is exposed to heat again, will remelt back into magma. Those are some changes to the normal cycle that make sense. There are some that don't make sense. For example, magma will never become metamorphic rock. Magma will never become sedimentary rock. Magma always cools into igneous rock. Okay? Igneous rock will never become sedimentary rock without first having broken down into sediment first. So there are some things you can skip and some things that you can't, and it all kind of makes sense, right? Any questions about the rock cycle? Great. Now, let's go back to our conversation about time and how Earth formed in the first place. The most popular theory right now in science for how Earth, or I should say how everything started, is the Big Bang theory. Okay? Namely, that at some point, right now we believe it to be about 13.7 billion years ago, there was an explosion of matter where there was no matter before. Okay? That matter, the most basic fundamental form of matter is hydrogen, right? It's the most simple atom that exists. This explosion of hydrogen, it sent hydrogen all through space, nothingness. Okay? Eventually, a whole bunch of hydrogen kind of congregated together. Why? Everything made out of matter has mass, right? Even a hydrogen has mass. It has an atomic mass of 1. You can see up there from our periodic table, right? Mass is drawn to mass. Do you know what we call that? What happens when one object of mass is drawn to another object of mass? Say it louder. Gravity. Bingo. Thank you, Kate. Okay, so we have gravity. And this gravity slowly pulls these hydrogen atoms together. And as more hydrogen atoms come together, what increases? The mass, and therefore gravity. And so more hydrogen is pulled down. And so you get these clouds of hydrogen pulled together until so much hydrogen is there that it collapses in on itself and it becomes a supercritical mass. And that supercritical mass, this cloud of hydrogen, makes the first suns. Okay? Or what we call a sun. They're actually called stars. Our sun is a star with a name. Do you know the name of our star? Sol. That's why we call our little grouping of planets around our star the solar system. There is no other solar system anywhere because our star is the only one named Sol. The other ones, we just call them star systems. Okay? Ours is the only solar system because it surrounds Sol. Okay? So you get all these stars, and these stars are doing something. They were formed through an incredibly concentrated amount of atoms and energy. And that supercriticality that started them did so by tearing those hydrogens apart. It ripped the proton and neutron away from themselves, okay? Or the proton and electrons and all of that. It ripped that apart. And what does it do with all that? It starts making new atoms. What's the process of ripping atoms apart called? Do you know? Fission. We use it all the time. Our nuclear reactors use fission. Our nuclear weapons use fission. It releases an incredible amount of energy. Okay? I forget what the exact number is, but the amount of fission that goes on inside of our sun at any given moment, every second, is equivalent to a couple billion nuclear weapons going off all at the same time, something like that. Yeah, we can't even come close to that much energy, okay? But it's releasing all that energy, and all that energy goes into another process, a process of taking all those broken pieces of the broken up atoms and making new atoms out of it. What do we call that? Huh? Fusion. Fission is the ripping apart of atoms. Fusion is the creation of new atoms. So in this first generation of stars, hydrogens get ripped apart, and then those pieces get stitched back together, except now we have a new atom that's formed. This new atom is what? It includes a few more particles than hydrogen did. What's number 2 on our periodic table? What's the next step up in, I guess you could say, complexity of atoms? Helium. These stars ripped apart hydrogens and put the pieces back together to make a slightly heavier element, helium. And then after it ran out of hydrogen, it ripped apart heliums. And what did it make? Lithium. This first generation of stars burned its way, when I say burned, I mean ripped apart and pieced back together, through hydrogen, making helium, lithium, beryllium. It started making heavier elements. That's why stars change the type of star that they are. A nice, early, hot star is burning hydrogen and helium and those earlier elements, okay? As their life goes on and they run out of those easy to burn, I guess you could say easy to burn, okay? Easy to rip apart and piece back together elements, they start going through a sequence of heavier elements and your star changes. Our star, it's about halfway through its life cycle right now. It will eventually become what is called a red giant. That is because it is no longer burning its current sequence of elements, okay? It's burning sodium right now, okay? Because it is not going to be burning that forever, it's going to, I think it's sodium. Yeah, I believe it's sodium. That's why it's got that white color. There are lots of different colors of stars, by the way. There are blue stars, there are red stars, there are orange stars. There are some stars that we believe are black, but I'm not going to go into that right now. There are no green stars, though. None of those elements that can be burned set off the wavelength green, which is very interesting. I wish there were green stars. Regardless, eventually, in about another 5 billion years, it's going to become a red giant. That's its next life cycle. It's burning heavy enough elements that it can't sustain that reaction in its current size. It's going to expand in size. Think of this as entering old age. Right now, it's in the prime of its life. When it enters old age, it is going to expand and encompass most of the inner part of our solar system. Earth, where Earth is right now in its orbit around the sun, it is going to be inside the perimeter of the sun in 5 billion years because it will have increased that much. Yes?
What element does it stop at?
Okay, so for a lot of these early generations of stars, it stopped, I should say, at iron. Okay, we call this the R process. It's the process by which all the elements all the way through iron were made inside of a star. All of those elements on those periodic tables were made inside of stars. This first generation stopped about at iron. Okay, now what happens to make all of these other elements? Okay, so when a star reaches the end of its life cycle, so it's gone through its life cycle, okay? So it's gone through red giant, and then two things will happen. It will either, at the very end of its life, blow up. Do you know what we call that? It's a nova, yeah? A nova is when a star blows up, and what happens to it? It spreads all those heavy elements that it spent all this time creating, blasts them through the galaxy, okay, through space. And then eventually all of those particles, those now heavier elements, will congregate together condense and make a new star, and that's where you start making the even heavier elements after that, okay? Or instead of going nova, it will kind of just die. Its energy will just kind of stop. Its reactions will stop, and it'll just kind of dissipate into this cloud. Either way, you end up with a whole bunch of heavier elements that have been spread through the galaxy, through the universe. And then they congregate again and go through the same process. Our sun is only a little older than our planet. By a little, probably like a billion years, okay? It's not in one of those first generations of stars. It's probably in the third generation of stars since the universe began, okay? Now, what's happened now is we've gone through all this periodic table, making all these elements. Some of these elements aren't in a gas form. They're in a solid form when they congregate together. And so when our star formed out of a series of elements, hydrogen, helium, all of those, not all of those elements got pulled in to make the star. We ended up with a star surrounded by a whole bunch of other debris caught in its gravitational well, but were not pulled into the star itself. The heavier debris got pulled closer to the middle, okay, and the lighter debris stayed further on the outside. That heavy debris in the middle made rocky planets: Earth, Mercury, Venus, Mars. The 4 planets here closer to the sun are made out of the densest material, that which made rocks. The planets further out, Jupiter, Saturn, Neptune, Uranus, those are gas giants. Okay, that lighter material stayed on the outside. Now you may ask, what about Pluto? That's a good question. What about Pluto? There are so many theories for what Pluto is and why it is here. Some of my favorite theories, some believe that it is a planet or a rocky body that formed in another solar system. That solar system died, its sun died, didn't go nova, just kind of like just died. And then because there was no gravitational body holding Pluto there anymore, it just kind of drifted off through deep space until eventually getting caught in the gravitational well of our own sun, which is why it's the only rocky body that far out on the other side of the gas giants. I love that theory because it's very fanciful, you know, to think that Pluto came from another solar system. We won't know until someone goes out there, I guess. Yeah.
Pluto older than our sun?
Don't know. Won't know until someone gets a piece of it. It'll be a long time until that happens. The amount of time it would take for someone to reach Pluto. Whew. And then even when you reach Pluto, what you do. Let me tell you something interesting about Pluto. Here's something that you'll learn about me. There are more tangents in my class than the calculus class down the street, okay? We're going to go on a lot of tangents in my class, all right? Here's the first one for the day. How about that, okay? Pluto, one of the reasons why Pluto was determined not to be a planet, I'm sure you all heard about that. This is a big decision they made about a decade back, is that Pluto has a moon, but that moon is large enough that they actually orbit each other. Okay, its moon is basically an asteroid that got caught in its gravity. Okay, but it's just slightly less than half of its size. I think it's like 30-something% of its size, which means that instead of the moon orbiting Pluto, they orbit each other. Yes, they're doing this. Okay, but here's the trippy part. Where is the center of gravity for Earth? The center of our planet is the center of its own gravity, which is why you and I are pulled towards the middle of the planet. Okay, if I was standing here and Sebastian, right? Okay, was standing in China, he and I would both be pulled towards the same point, the center of our planet. That's where the center of gravity is. For Pluto, because it is orbiting another body, aka its moon, they are orbiting each other, the center of gravity for Pluto is not at the center of Pluto. It's in space between itself and its own moon. So if, by any chance, you were able to land on Pluto, guess what? You wouldn't stay there. Gravity would pull you into space between it and its own moon. No one will ever walk on Pluto unless you happen to be on the other side of the planet, exactly opposite the vector between it and its moon. No one's ever going to be able to just take a stroll around Pluto because you get pulled off into space. Yeah, exactly. The moon is going to pull you away from the planet. Okay, so that's one of the reasons that orbital relationship is one of the reasons why it's not considered a planet. Okay, so as far as ever getting samples off of Pluto to figure out exactly where it's from and how old it is, I still don't know how that's going to work out. It's science fiction at this point because it's so far out and we know very little about it still. Tangent over. Okay. So this whole thing is called the nebular body. Okay. So you start with kind of this nebulous gas cloud. It condenses to form a sun. You get these concentric rings of debris. Those debris rings, eventually all that debris crashes into itself and you form a planet. Okay. Some of that debris formed rocky planets. Some of that debris formed gas giants. And so at the end, what you end up with is a ball of just superheated debris that eventually cooled off enough to become our planet. Okay, that's where Earth was formed from. So how old is the Earth? 4.543 billion years. I need to print more of these, I guess. It's all right. Let's talk about numbers. How many of you have a coin in your pocket right now? Just a couple of you? Okay, coins, that's becoming a lost currency medium. Okay, most of the time we use digital currency these days. Okay, cents. Okay, we still use cents even though not many of us use coins. We think of those. Okay, we think of in terms of lifetimes, usually tens, hopefully 100, right? If we can swing it, right? And life is good. All right. We think in terms of salaries, tens of thousands of dollars. Hopefully, more than that. Unlikely with our economy, but hey, there we are. Okay. We think in terms of the US budget, which, yes, is in billions of dollars, but who even blinks twice if the US says, yeah, we approved another $6 billion budget? That'll get us through to December, right? Maybe not even that long. No one even thinks about that anymore. So let's talk about exactly how big 1 billion is. Okay. How many dots do I have on this sheet? I don't actually expect you to count. Someone just please throw out numbers. 823? 10,000. Wow. What else? Anyone want to venture anything between 823 and 10,000? Or less? 1,000? Anyone else? No one? What do you think? Well, I'm sorry, what was your name again? Zara. Okay, Zara, what do you think? How many dots are on there? 15,000. Wow. Okay, no, that's 4,000 dots. Okay, so here I have a sheet of paper. It's that sheet that we looked at earlier. This sheet of paper has 4,000 dots on it. Okay, they're actually little asterisks if you look close enough. So how many sheets of paper would I need to reach 1 million dots? Yes, I am asking you to do math. Pull out a calculator if you need it. Huh? No. No, there's 4,000 dots here, and I need you to tell me how many pieces of paper I need to reach 1 million dots. Divide 1 million by 4,000. That's fine. Pull out a calculator. Do it. This is interactive. I teach this class not to talk at you. I talk with you. Yes. 250 sheets of paper to reach 1 million dots. Perfect. Now, right here, this is a ream of paper. That's what you call one of these bundles of paper. This is a ream of paper with 500 sheets in it. We need half of that paper to reach 1 million dots. One ream of paper, we'll come back to that in a minute. How many sheets do we need to reach 1 billion dots? Yeah, you really need a calculator for this one. How many more zeros are after 1 billion than there are after 1 million? There are 3 more zeros. So just throw 3 zeros on the answer you got before. Was it? 250,000. Okay, you're on the right track. 250,000 sheets of paper like this, right? To reach 1 billion dots. That's going to be 500 reams, each of which is about 2 inches and change tall. 500 reams of paper. That's a tower of paper 83 feet tall. But we're not talking about a billion, are we? How many years old is the Earth? 4.543. That will give us 2,250 reams, each of which contains 500 sheets of paper, each of which has 4,000 dots, each of which represents 1 year of Earth history. That's a tower of paper 380 feet tall. That's a lot of years, isn't it? That's how old the Earth is. It's impressive. Okay, I'm going to beat the dead horse. Let's have another example. Who needs to stand up and take a walk? Good. We're going to go walk around the planet. We're going to take a walk around the planet. I hope you all brought your Fitbits. Okay. How many times would we need to go around the planet to reach 1 billion? Well, the average human step is about 2 feet. Okay. That's for the average size person. Some people will be less, some people will be more. That's just average. Okay. So at that rate, 1 billion steps would require you to go 15 times around the equator. But again, we're not talking about 1 billion. We're talking about 4.543 billion. That's 70 times around the equator. You ready? No? What if I put extra credit on it? Yeah, count you in. There you go. Right? Okay. Are we all a little clearer now? Exactly with the scale that we're talking about. A lot can happen in 4.5 billion years, right? We're going to talk about some of those things that happen in this class and in the next class, assuming you take that one, okay? Now, let's talk about geologic time itself and how we separate geologic time. Everyone pull out some paper and pencils. If you don't have paper, I've got paper. I don't think I really have pencils, or pens. You could use a pen. Let me know when y'all are ready. Man, it looks like everyone's got it. My online students, by the way, if at any point I'm moving too fast for you during this, you know you can always pause it and then just do what I ask and then turn it back on. Okay. In this far left column, you are going to write these words. These words exactly. Okay, we're not working with any dates yet. Okay, just these words. Started college, started high school, started grade school, learned to ride bikes, learn to walk, born. Born at the bottom, right? By the way, why do I have it organized with born at the bottom instead of born at the top? The law of superposition. Look at you guys. Good. Oldest on bottom in geology. Okay. Give you a minute to write those down. Okay. Now in this middle column, that's when we're going to put the years associated with each of those events. These are my personal years. Put your own. What was that face? Oh, he's so old. I'll spare you all the time doing the math. I am 30 years old. Okay. Now, I want you to draw a horizontal line between when you learned to ride a bike and when you started grade school. How we doing? We all caught up? Okay. Above that line, in that last column, write the word Schoolian, and beneath it, Preschoolian. What have I done here? I have used events of my life, and each of you, events of your own lives, to separate the periods of time we've been alive thus far into two distinct time periods. That which occurred before you started school and that which occurred after. This is how we separate geologic time. The Triassic, the Jurassic, the Cretaceous, the Permian, the Ordovician, all of those names, all those time periods are separated from each other because of distinct events that occurred before which something was one way and after which it was a different way. Perhaps we see the first trees. Perhaps we see life leave the ocean. Perhaps we see the extinction of 50% of all life on the planet. Whatever it is, we draw that line and separate that time from that which comes after. Okay? I could draw that line based on any of the events. I could put it right here. I could put that line right here and say anything below that line is Infantonian, for example. Or I could put it, and I could call everything right here, I could call that the Walkian. I could name it whatever I want based on whatever the difference is, right? I could put it right here. And above that line, I could call it the Collegian. And below that, the High Schoolian, whatever I want to call it. That's how we separate geologic time. Okay? So we use sequential life events, numerical time, and then we separate them based on those life events into time intervals. So here we've got a geologic time scale using aeons, eras, periods, epochs, years, and biological events. Epochs, however you want to pronounce that. Okay, I've heard it both ways from professionals. Okay? These are some biological events that cause scientists to draw those lines. This one, first reptiles, cockroaches, and mayflies appear. First one sounds good. The other two we could do without, right? But they're still important in our ecosystem, okay? Right here, gymnosperms, amphibians, dominant, beetles, stoneflies appear, okay? Right here, the origin of mammals. Ooh, that's a big one, isn't it? Very personal for us, right? So that's a great reason to draw a line there, okay? Based on life events that we can see in the geologic and fossil record, that's how we distinguish these geological time periods. Any questions? No? Clear as mud? Clearer than that, hopefully. Here's something else that you'll quickly learn about me. I make really bad dad jokes. So if I sense that people are kind of fading, I will bring out the dad jokes. You have been warned. All right? How did the hipster burn his mouth? He ate pizza before it was cool. Huh? Yeah? All right. So, the eons, the eras, the periods, and the epochs, those are the time intervals. Okay? Numerical time, that's the years that we put, right? And then sequential time, which for you was born, started school, rode a bike, whatever. Those are like the biological events that we have here. The exact same way we separated your life is the exact same way that we separate geologic time. All right. Let's talk about what's inside our planet. Later on in the semester, you'll learn about how we know that. For now, just take for granted that we know what's down there, okay? So we've got different layers inside of our planet. We've got the core, which is actually the inner and outer core. We'll talk more about that in a bit. The core is mostly made out of iron and nickel. Okay, extremely dense metals. There's also a lot of uranium down there, a bunch of other highly radioactive, highly dense materials, but it's mostly iron and nickel. Okay, the lower mantle is magnesium and iron, and then there's the upper mantle, which is also magnesium and iron, mostly the same composition as far as we know, with slightly different states. We'll talk more about that in a moment. Then we've got the crust being the most pertinent to us, right? We live on the thing, right? The thinnest section, but most important to us. It is mostly made out of 8 elements: silicon, aluminum, calcium, sodium, potassium, oxygen, iron, and magnesium. Why do you think it is made out of those 8 elements? I mean, yes, they are all utilized in life in some way. That is true. That's not why they're on the surface, though. Yeah. They're what? They are abundant on the surface. A lot of these are much rarer on Earth than say iron, nickel, magnesium, those. These 6 in particular, the silicon, aluminum, calcium, sodium, potassium, and oxygen, those are the ones that I'm looking at most specifically. Why are those 6 in such high quantities on the surface as opposed to, say, iron and magnesium? Why isn't the mantle rich in those things? Why is the crust? Okay, you said weight. Okay, now this is the thing. This is, you know the difference? Can someone tell me the difference between weight and mass?
Mass relative to space.
Mass is how much matter an object contains. Basically, the total sum of the elements that it contains. Okay? What is weight? It's dependent on gravity. Weight is that mass, and then there's the gravitational constant of whatever body you are on or near. If you were on the moon, your weight would be different from the weight that you have on Earth. It would be way less. Yeah. I weigh 200 pounds here. I'd weigh closer to, I think it's somewhere between 40 and 50 pounds. No, less than that, actually. It'd be between 20 to 30. Yeah, pounds on the moon, which is why you can see videos of astronauts jumping like 6 or 7 feet up and then slowly falling back down, right? Huh? Yeah, the equipment that they're wearing is extremely heavy, but they can just boom across the moon's surface. Why? Because they weigh less. Weighing less sounds good, doesn't it? Here's the problem, though. You still have the same amount of mass. You could weigh 400 pounds and be incredibly obese on Earth, and then go to the moon and weigh less, but that doesn't mean you have less. Yeah, exactly. Okay, so remember that. Mass is different than weight. Weight is dependent upon gravity. Okay, but you're on the right track there. Okay, these 6 elements, silicon, aluminum, calcium, sodium, potassium, and oxygen, are less massive, and yes, on Earth, weigh less than iron and magnesium. So they stay where? They are mostly on the crust. Okay, there's a lot of silicon and oxygen kind of all throughout the Earth, but aluminum, calcium, sodium, potassium, oxygen, a lot of those remain on or near the crust, and most of the crust is actually silicon. I actually have it broken down, silicon and oxygen. I have broken down right here. The crust by composition, 46% oxygen, 27% silicon, 8% aluminum, 5% iron, 3.6% calcium, so on and so forth. All of that's there. That's what our crust is made out of. The oldest, but why is it here? Because the heavy stuff gets pulled towards the center of gravity and the lighter stuff stays closer to the outside. Okay? Okay, so the oldest crust that we have on the Earth, we can find really old crust on Earth in 2 places. The Northwest Territories of Canada has 4 billion-year-old rock. I have a piece of rock from Canada that is about 3.6 billion years old. And then Western Australia has the oldest rock on Earth, 4.4 billion years. Does that sound right? The oldest rock we have on Earth is 4.4 billion years. So what's wrong with this picture? I just gave you a 10-minute lecture about how old the Earth is. How old was it? 4.543. And yet the oldest rock that we have on Earth is 4.4 billion years old? How do we know that the Earth is 4.543 billion years old? Any ideas? Mm-mm. Huh? Mm-mm. No. There are no fossils that old. We'll talk about fossils later. But rocks from. The oldest rock on Earth is 4.4 billion years old. The oldest rock on Earth is 4.4. So how do we know that the Earth is 4.543? What other source of rock could we have nearby? The moon. The oldest rock we found on the moon is 4.543 billion years old. The moon is made out of rock from Earth. Ergo, logically, the Earth must be at least as old as the moon. Logic, right? So that's where we get that number. So our crust, pretty thin, around 7 kilometers in the ocean crust. Also, here's another disclaimer. We use the metric system in my class. I will give you conversions to the imperial system of miles and feet whenever I remember. I may not remember all the time. I apologize. But in science, we use the metric system. Okay? So Earth, the crust, I should say, is about 7 kilometers thick. Okay? That's about 5 miles, give or take. Okay? And it's mostly made out of type of igneous rock, which we call basalt. You'll learn more about basalt next week. Okay? The continental crust, on the other hand, is far thicker, about 35 kilometers thick, okay, on average. It is a lot thicker on mountain belts. It can be thinner in some places, all right, but on average, about 35 kilometers. And this is its composition, as we already talked about, okay? Now, the mantle is the next layer down. It comes in 2 layers, the upper mantle and the lower mantle. The upper mantle is significantly thinner. The upper mantle is solid, but hot, okay? Mostly iron and magnesium-rich minerals, okay? The lower mantle is even hotter, mostly the same composition as the upper mantle, but here's where it changes. Because of the incredible amount of heat, it should be melted. Why isn't it melted? Why is it still solid when it is hot enough to be melted? It's compacted by what? Pressure. It is so incredibly pressurized at that depth that even though that material is hot enough to be melted, it is under too much pressure for the solid to become a liquid. It is forced to remain a solid. And so it is what I refer to as squishy. Think Play-Doh. Play-Doh, solid or liquid? Solid, but malleable. You put pressure on it, it will change its shape. The same is true with the lower mantle. It is solid, but under so much heat that it really should be melted, but it can't be melted because of the pressure, and therefore it is kind of squishy like Play-Doh. And so it is pushed and pulled and changed and forced and moved around, and it is that process, it is the fact that it's in that state that causes something that you're going to learn about later called convection, and that's what causes plate tectonics. That the movement of the pressure pushing that solid material like that is going to cause motion in the upper mantle above it, which in turn causes motion on the bottom of the crust, pushing our tectonic plates around. Of course, yes. Okay. Underneath of that is the core. How many of you have seen this movie? You have? It's fun. This is one of the movies that we will have the option of picking for our movie night. Okay. It is truly ridiculous. Love it. Okay. Now, the core is separated into two sections, just like our mantle. You have got the inner core and the outer core. The outer core is the only liquid layer on our planet. How many of you learned in grade school or even high school that underneath the crust is an ocean of magma? Most teachers still teach that. We know better now. We've known better since the late 60s, but it takes a long time for such knowledge to percolate down through all of the education systems. The only completely liquid layer on our planet is the outer core. This is an iron-nickel alloy. Notice it is no longer iron and magnesium. We are working with way denser metals now, okay? It is so incredibly hot in the outer core that it overcomes the pressure and we have a liquid layer, okay? And then when you get to the inner core, excuse me. When you get to the inner core, the pressure is increased so much again that it overcomes the heat. And even though it is incredibly hot, it is now in a solid form. So you can tell, the deeper you go into the earth, you've kind of got this battle between the heat and the pressure. Is it going to be liquid? Is it going to be solid? Okay, we got solid, solid, liquid, and then back to solid because the pressure became so great again. Okay? So the interaction between the inner core and the outer core, where our outer core is liquid iron and our inner core is solid iron, both of which have magnetic properties, right? You know how magnets are basically electrified. It's basically electrified iron, right? That's what a lot of magnets are. They are both magnetic. And because we have a solid mass of iron inside of a liquid mass of iron, and this liquid mass of iron is flowing and moving, and this thing's probably moving too, by the way. Very little proof that we can use to prove it, but the properties of our planet's magnetic field suggest that our core is also rotating. Earth is spinning. Our inner core also is probably spinning, but probably in a different direction to the rest of the planet because it's inside a buffer of liquid. So it doesn't have to spin the same way that we are. Imagine if I had a bowl of water here, and in that bowl of water, I put a golf ball. My golf ball is floating in my water, right? What happens if I spin the bowl? That golf ball doesn't necessarily need to spin with it, does it? It's in a buffer of water. It's not touching the bowl itself. Neither is our core. It's in that buffer of liquid iron. So it's probably got some spin to it, maybe generally in the same direction as the Earth, but not necessarily at the same rate or speed or anything like that. And so because of the interaction of this solid and liquid iron rotating against each other, that's what generates our planet's magnetic field. That magnetic field, which we have around our planet, saves us from the vast majority of solar and cosmic radiation that would burn our planet to a crisp. Think about it as our planet having its own personal force field. Okay, that's essentially what it does. Okay, it diverts most of that radiation away, makes it flow around the planet. Okay, any questions about the core?
You feel like they both have like magnetic, like the ball and they pull or like.
So that's a hard question to answer because there's a lot that goes into it. You're thinking about refrigerator magnets, okay, as far as push and pull. That has to do with the poles on your magnet. Negative and positive poles are drawn to each other. Have you ever had a magnet where that was repelled by another magnet? Okay, that's because you were trying to push a positive towards a positive pole or a negative towards a negative pole. They are only drawn to each other if you flip them around and go negative to negative and positive to positive. Okay. As far as positive and negative poles in the core are concerned, I don't even know how to begin answering that, right? Because that's liquid for one thing, and that's a sphere. So I don't think that there are any true set poles, so to speak. And if there are, it might resemble what our north and south poles are on the outside of our planet, where this could be the south pole and that could be the north pole, for example. But I can't confirm that to you, and I don't know if anyone really can. Fair enough? Okay. We'll talk more about Earth's magnetic north and south later on in the semester. Yeah, absolutely. Okay. Our continents are mostly made out of rock from those lighter elements, the calcium, sodium, potassium, right? Silicon, oxygen. Okay. Your ocean rock, okay, your ocean crust is mostly made out of the darker or the heavier elements. Okay, so you've got your irons, your magnesiums. Okay. What does this mean? There's a difference in density. Lighter minerals here, less dense. Heavier minerals here, more dense. And this is why ocean crust has water on top of it, and continental crust rides kind of higher up on the mantle than the ocean crust does. Continental rock is above the ocean water because it is less dense on top of the mantle than the ocean crust is. It doesn't have the water on top of it because it is less dense. If we only had this material across our entire planet, all that water would probably be evenly distributed. Right. If we had no tectonics and it was all just that same material, it would just be, the oceans would be a lot shallower, but it would be all over the planet. But because we've got this distinctly less dense material making our continents, the continents are kind of pushed up. They are more buoyant on top of the denser material of the mantle than the ocean crust is. Okay? So it's not that big of a difference in density. Continental crust, 2.7 grams per centimeter cubed. Ocean crust, 3.0 grams per centimeter cubed. By the way, you're all familiar with what I mean by density, right? Density is a measurement of mass per unit volume. Okay? So here I have the same ship, okay? But it's occupying the same volume, right? But in this one, I filled it with cargo containers. Notice that this ship with all the cargo containers is riding way lower in the water than the ship without them, occupying the same volume, but this one contains more mass, therefore it is more dense. Okay, that's what I mean by density. Okay, let's talk about mountains. Mountains are the result of tectonic plate activity. Normally, tectonic plate collisions, where two plates crash into each other, you often get a mountain range. We'll talk more about that later. The two major mountain belts that we have in the world right now are the Circum-Pacific Mountain Belt, which comes around Antarctica right here, up through South America, along North America, over through Alaska, and then comes down here and ends up around here, okay? The Circum-Pacific, or around the Pacific Mountain Belt, okay? The other one is the Eurasian Mountain Belt, which comes across Africa and Eurasia all the way through here and kind of runs into the Himalayas right there. Okay, those are the two major mountain belts that are being grown at the moment because of current tectonic activity. Okay, there are some older mountain belts as well. These purple ones, these are older ones, okay, older mountain belts. Anywhere you see on this map that is pink, those are mountain belts that are so old that they've been weathered and broken down all the way down to ground level. But we can still see that the rock present there at ground level was once inside of a mountain belt. And everywhere you see that's this kind of grayish beige color, that's basically the same thing as the pink, really old mountain belt material, but now it's covered by sedimentary rock because it's even older. So let me ask you this. Based on this color-coded map, what can you tell me about the continents? Okay, so two of you spoke. Let's start here. They're constantly shifting and moving over time. That is true. Not what I'm going for, but very true. Okay, so that's basically coming off the same thing he is. There were once one. That is also true. We will talk more about that. Not what I'm looking for at the moment, but hold that thought for a later lecture. I told you that yellow, pink, purple, and that gray color are all remnants of a mountain range at one point or another, right? Is there anywhere, any continent on this map that is not one of those colors? No. They are all completely one or more of those colors. What does that tell you about continents? They are made by what? They're made by mountains. There is nowhere on any continent anywhere on Earth that was not at one point pulled out of the ocean through the creation of mountain ranges. The earliest continents were in fact just mountains rising from the seafloor. We talk more about that in 1404, but it's a truth that you need to be aware of for this class as well. Okay. I just went over that. Okay. Now, off the coast of these continents we're moving into ocean basins. Okay. We have what is called a continental margin. Continental margin is separated into a couple of different sections. Your continental shelf, that's very shallow water. This is actually continental crust that is sometimes exposed. When water levels fall, or this continent is pushed out of the ocean a little bit more, that becomes continent. Okay, so it's basically flooded continental material. During an ice age, these are usually exposed. If you look at that map over there, or if, say, my online students were to look at any map of the United States with seafloor elevations, you'll see that particularly around the Yucatan Peninsula, the East Coast, and Florida and the Bahamas, you see those white halos around the current continental margins. That's basically continental landmass that is currently underwater. Those white sections are exposed during ice ages because there's so much water in the ice that is not in the ocean, and so sea levels drop. That's all exposed. You can drill into that rock and you can find bones from animals that were living there during the last ice age out in the ocean. Okay. Then further out into the ocean, you've got your continental slope. This is the sort of ramp of going down from continental material out into the ocean. And then your continental rise is when you're going out into the deep ocean basins. Okay, so that's how we progress from continent into ocean. You go through that process. Continental shelf, then slope, then rise, and then finally you're out in the deep ocean. Now, what's out in the deep ocean? Not a whole lot. Some seamounts, which are underwater volcanoes. There are lots of them, by the way. How many of you saw that Tonga eruption last year? Yeah, okay. It was pretty dramatic for the people of Tonga. Covered pretty much their entire island in ash. They're still recovering from that. Tonga's main financial reliance is tourism, and their island got covered in ash. So they took a major financial hit. But this was from a volcano only a few miles off of their coastline that was underwater. And it blew up, sent a tsunami into their capital, and covered them in ash. One of about 2 million underwater volcanoes that we just can't watch all of. There's no way we could watch all of them. And sometimes that bites us in the butt. But there's a bunch of volcanoes under the water is my point, okay? Then you've got your trenches. And abyssal plains are basically just long, flat, boring expanses of not a whole lot, broken up by the occasional volcano or shipwreck, okay? Then you've got your mid-ocean ridges. And mid-ocean ridge is a rift between two plates. Normally, where two plates are splitting apart from each other. Two tectonic plates are moving away from each other instead of towards each other. So you get this sort of trench with volcanic activity on each side, okay? So the mid-Atlantic ridge is where the two sides are moving away from each other, and you've got this sort of trench here, and you've got volcanic activity on both sides, and it runs right through the middle of the Atlantic Ocean, hence the name Mid-Atlantic Ridge, okay, right through there, and it slices the nation of Iceland in half. Iceland is a volcano volcanic island that has built up on each side of that mid-Atlantic ridge. I went to Iceland in 2017 and was able to go scuba diving inside of that rift where it slices Iceland in half. So for a very short period of time, I was touching no tectonic plate. It was very cool. And then if you go further along that valley, there's a place where the two plates come extremely close together. And for a moment, I was able to touch two tectonic plates at the same time. Iceland is an amazing place. Highly recommend you go. Okay, especially if you're a geologist. It's a geologist daydream. Like you've got glaciers, you got volcanoes, you got rift valleys, you got all sorts of stuff going on there. Kept me busy for a week, and I only saw like 25% of the island. So where these plates are breaking apart, we've got plate boundaries, which I will talk about on this next slide here. But the theory of plate tectonics is simply this. Earth's surface is broken up into a series of lithographic plates, that is, plates made out of rock. And they are moving around based upon convection currents underneath of them. Convection, to understand convection, all you need to know is that heat rises. Is that true? Do we all know that's true? That's true in gases, solids, and liquids. Particularly here important to us is the solid part. The mantle is solid, true? We already just learned about this. The mantle is solid, but it is still subject to convection. That is, hot mantle material from deep underground rises up towards the surface and then gets pushed to the side by newer, hotter rising material beneath it. And as it cools off, it becomes more dense and sinks back in, where it will get reheated and pushed back up to the surface. This all takes hundreds of millions of years, right? But it's creating drag on the bottom of our tectonic plates. And that's what causes tectonic plate movement at the surface. So we've got 7 major tectonic plates: the North American, South American, Pacific, African, Eurasian, Australian, and Antarctic plates, plus a couple dozen smaller ones, okay, stuck in between them. And they collide with each other, they pull apart from each other, and they drift past each other. When they collide, we call it a convergent plate boundary. They crash into each other. They are converging, okay? Then you've got a divergent plate boundary where they're splitting apart from each other. And then when they're scraping past each other side to side, that's called a transform plate boundary. An example of a convergent plate boundary is when India hit Eurasia. India is its own subcontinent. It's on its own plate. And a while ago, about 56 million years ago, it crashed into the main continent of Eurasia. And that's why we have our Himalayan mountain range there. That mountain range is a result of that collision. Okay? Then you've got divergent plate boundaries where they split apart from each other, like that mid-Atlantic ridge I just talked about. Transfer plate boundaries where they scrape past each other, that makes a lot of earthquakes. Okay? The San Andreas Fault is an example of this sort of movement. Okay? Transfer plate boundaries create a lot of earthquakes because there's a lot of friction that builds up here along this boundary. Any questions about anything at all today? Nothing? What do y'all think? How are y'all feeling about the class? You like it? Yes. All right, well, I guess if you like it, I do too. All right. Well, that's all I got for you today. So here's a fun little thing that you can do, okay? Sometime between now and Thursday, I want you to find a rock and then bring it to class. And for my online students, you can do this exercise as well. Find a rock. You can send a picture of it. You can post a picture of it. Actually, here's what you do. Post a picture of it in the next Go React on Thursday when you're responding to something, okay? Just post it there. I want you all to bring your class. It'll be at your seat here in this classroom for the rest of this. And by the end of the semester, you're going to tell me what it is. Just a fun little personal exercise. I guarantee it'll be less challenging than some of the other things I throw at you. So, any questions? All right. Well, I'm going to go ahead and end this here.